Picture a night sky so dense with stars, it looks like spilled glitter across black velvet. Now imagine not one, not two, but 12 suns tangled in an intricate dance, their light weaving through the cosmos like threads of fire. This isn't science fiction, it's the reality of duodecuple star systems, some of the most bizarre and bewildering structures in our universe. For centuries, astronomers believed multiple star systems were rare curiosities, but now we're uncovering clusters where a dozen stars orbit each other in chaotic, mesmerizing harmony. And what we've learned so far, it defies everything we thought we knew about how stars live, die, and interact. Think about the complexity of a single star like our Sun, its gravity, its storms, its delicate balance of forces. Now multiply that by 12. The gravitational pulls in these systems aren't just competing, they're warping spacetime itself, creating zones where time slows down, light bends into knots, and planets, if they exist, would experience days with 12 sunrises and sunsets. Some of these systems are so unstable, stars slingshot past each other at unimaginable speeds, while others move in rhythms so precise they could be clockwork crafted by the cosmos. And here's the strangest part. We've found over 50 jaw-dropping anomalies in these systems that challenge the very laws of physics as we understand them. What could possibly explain a star system where 12 suns don't just coexist but thrive in a ballet of light and gravity? That's the mystery we're unraveling today. From stars that steal matter from their siblings to black holes lurking unseen in the chaos, each discovery in these systems rewrites the rules. By the time we're done, you'll see the night sky differently. Because once you know what's lurking in these celestial families, you'll realize the universe is far wilder, far more inventive than we ever dared to dream. So let's begin where the ordinary ends and the extraordinary takes over. Strap in, we're diving deep into the enigma of duodecuple star systems. The first known duodecuple star system wasn't just a scientific breakthrough, it was a cosmic revolution. Astronomers stumbled upon this celestial oddity while combing through decades of telescope data, their instruments revealing not the expected single or double stars, but a dizzying 12 suns locked in an intricate gravitational embrace. The discovery hinged on two key techniques: radial velocity, which detects the subtle wobble of stars as they orbit one another, and transit photometry, catching the telltale dips in light when stars cross in front of each other from our vantage point. Together, these methods painted a picture so complex it shattered previous assumptions about stellar groupings. Located nearly 5,000 light-years away in the constellation Cygnus, this system behaves like no other. Instead of neat, hierarchical orbits, its stars move in intersecting planes, some pairs circling tightly while others swing wildly in sprawling loops. Early models predicted such configurations would collapse under their own chaos, yet here they were, a gravitational high-wire act lasting millions of years. One particularly baffling trio at the system's heart defies logic. Two massive blue stars pirouette around a shared center, while a smaller red dwarf darts between them like a cosmic hummingbird, its path erratic yet somehow stable. What makes this discovery even more extraordinary is how it forces us to rethink star formation itself. Conventional wisdom said stars born in crowded nurseries either merged quickly or flung each other apart, leaving behind simpler systems. Yet this duodecuple arrangement suggests stars can somehow negotiate fragile truces across vast distances, their motions balanced on a knife's edge between order and mayhem. It's as if the universe took our textbook models, crumpled them up, and tossed them into a black hole, replacing them with something far more wondrous and strange. Gravity behaves differently when 12 stars crowd into a space smaller than our solar system. In most stellar systems, orbits follow predictable paths governed by centuries-old equations. But in duodecuple systems, the rules break down spectacularly. Picture a cosmic mosh pit where stars don't just sway, They shove, grapple, and occasionally fling one another across the void. Astronomers call this gravitational chaos, and it's rewriting our playbook for how celestial bodies move. Take the system catalogued as HD 1256, where 7 stars orbit within a region barely wider than Jupiter's path around our Sun. Simulations show their dance isn't just unstable, it's mathematically chaotic, meaning tiny shifts in position today can lead to wildly different trajectories centuries later. One star might swing peacefully for millennia, only to suddenly catapult toward its neighbors at a quarter of light speed. What keeps these systems from tearing themselves apart? Surprisingly, it's their own pandemonium. The same turbulence that destabilizes orbits also creates brief moments of balance, like a spinning top finding fleeting stability mid-wobble. Then there's the case of K991, where 3 pairs of binary stars spiral around a shared center while 6 lone stars weave through them like thread through a needle. Telescopes caught 2 of these loners passing within half an astronomical unit closer than Venus orbits our Sun, yet neither star was torn apart. Instead, their gravity twisted into a temporary knot, bending their paths into pretzel shapes before flinging them back out. This isn't just orbital mechanics, it's gravitational improvisation, where stars follow no sheet music but somehow create haunting cosmic harmonies. Advanced simulations reveal even stranger behavior. When modeling the quintuple star subsystem within T-Upsilon 47, researchers watched in disbelief as one star's path resembled a spirograph drawing gone wrong, looping inward, then lurching outward in jagged steps. The culprit, so-called gravitational kicks from its siblings, which pile up like missed notes in a symphony, warping its orbit beyond recognition. Yet against all odds, these systems persist for eons. Some theorists argue their very chaos acts as a shield, preventing any single star from gaining enough leverage to dismantle the group. What does this mean for our cosmic rulebook? Traditional two-body equations fall apart when 12 gravitational heavyweights crowd the same backyard. New models incorporating n-body chaos suggest these systems might be far more common than we thought, hidden in plain sight, their turmoil mistaken for observational noise. Every flicker of light, every irregular wobble could be a duodecuple system whispering its secrets. And if that's true, the universe might be teeming with stellar families far stranger than we ever imagined. Stars born into duodecuple systems don't get the luxury of peaceful middle age. They live fast, die young, and go out in spectacular fashion. The constant gravitational tug of war and intense radiation baths in these crowded systems create stellar life cycles that make our Sun's steady existence look downright boring. Where a solo star might burn calmly for billions of years, stars in these chaotic neighborhoods often exhaust their fuel in a fraction of that time, some blazing through their entire evolution in just a few million years. Take the hypergiant star catalogued as V138 in the system MSI-12. This monstrous beacon shines with the brightness of 5 million suns, its outer layers perpetually stripped away by the gravitational harassment of its 11 siblings. Normally, a star of this mass would live for perhaps 6 or 7 million years before collapsing into a supernova, but in this system, it's already showing advanced decay after barely 2 million years. The culprit, constant tidal forces from neighboring stars act like cosmic sandpaper, eroding its atmosphere and funneling material away at staggering rates. Telescopes have caught streams of glowing gas arcing between V138 and 2 smaller companion stars, a stellar transfusion that's simultaneously feeding its neighbors while starving the hypergiant itself. Then there's the case of the supernova factory in system Kappa Omega 9, where 3 stars have exploded in the last century alone. In typical galactic regions, you'd expect 1 supernova per century per galaxy. But in this duodecuple system, the density of massive stars and their gravitational interactions create perfect conditions for chain reaction stellar deaths. The first explosion in 1942 actually triggered the second shockwaves from the initial supernova compressed nearby stellar material, causing an unstable neighbor to collapse just 18 years later. Now astronomers are watching a third star, its core destabilized by these events, expected to detonate within decades. The violence doesn't stop at supernova. Some systems produce kilonova, ultra-powerful explosions when neutron stars merge. In System T-481, two neutron stars orbit so closely that gravitational waves bleed their energy away, drawing them inevitably together. But their dance keeps getting disrupted by passing siblings, which yank on the pair unpredictably. Current projections suggest their final collision could happen tomorrow or in 100,000 years. A celestial Russian roulette where the bullet is a burst of gamma rays powerful enough to sterilize entire galaxies. What's truly mind-bending is how these systems recycle their dead. In more sedate regions of space, supernova remnants drift apart over millennia. But in duodecuple systems, the gravitational web traps ejected material, funneling it into accretion disks around surviving stars. System X922 provides the ultimate example. Spectroscopic analysis shows a newborn star that contains traces of at least 3 distinct supernova events, meaning this stellar infant is quite literally built from the ashes of its dead siblings. It's a cosmic circle of life so dramatic, it challenges our very definitions of stellar birth and death. If planets exist in duodecuple star systems, they'd experience cosmic real estate unlike anything in our solar system. Imagine a world where the sky holds not one sun but 12, some blazing close enough to cast quadruple shadows, others flickering like distant lanterns in an ever-changing celestial dance. The very idea challenges our understanding of planetary formation, because traditional models suggest such chaotic environments should rip protoplanetary disks apart before worlds could take shape. Yet theorists argue that under just the right conditions, planets might not only form in these systems, they could survive there, though their orbits would defy all convention. Take the disputed observations from System Zeta Tau 12, where astronomers spotted rhythmic dips in starlight that matched no known stellar behavior. Some researchers believe these could hint at a gas giant trapped in what's called a gravitational sweet spot, a narrow zone where the competing pulls of 4 parent stars balance just enough to permit a stable, if highly eccentric, orbit. This hypothetical planet wouldn't follow a neat ellipse around any single star. Instead, it would trace a wild, loopy path like a marble rolling through a maze of gravity wells, its speed fluctuating wildly as different stars took turns dominating its motion. Seasons on such a world would be incomprehensible, with temperatures swinging from scorching to frigid in hours as it veered between stellar heat sources. Simulations reveal even stranger possibilities. In one modeled scenario, a rocky planet gets caught in a figure-8 orbit around 2 close binary pairs. For centuries, it might enjoy relatively stable lighting from its primary stars until a distant 5th star tugs it off course, sending it careening toward another gravitational anchor. The planet could spend millennia as a frozen rogue before being recaptured, its atmosphere alternately boiled away by proximity to one star and then frozen solid in the depths of interstellar space. Life here would need to be unimaginably resilient, enduring conditions that flip between oven and freezer on cosmic timescales. Then there's the tantalizing and hotly contested infrared signature from System Lambda Epsilon 7. Some speculate it shows debris rings that could indicate shattered planets, their remains pulverized by gravitational tides. Others argue the signal might instead be protoplanetary materials stubbornly clinging together despite the chaos, hinting at worlds in the earliest stages of formation. If confirmed, it would mean planets can emerge even in these gravitational war zones, perhaps in sheltered pockets where clusters of stars create temporary calm. The ultimate wildcard, tidal locking. In quieter systems like ours, planets often settle into synchronous rotation, keeping one face permanently toward their star. But in a duodecuple system, competing gravitational forces could make a planet's rotation erratic, spinning rapidly for centuries before abruptly reversing direction. Days might stretch or shrink unpredictably, with sunlight glaring from multiple angles in a disorienting celestial strobe. While no definitive exoplanet has been confirmed in such extreme systems yet, their potential existence forces us to expand our definition of habitable. If life can cling to hydrothermal vents in Earth's deepest oceans, who's to say it couldn't adapt to a world where the rules of physics seem rewritten daily? These hypothetical planets, should they exist, would be testaments to nature's stubborn creativity, pockets of order thriving in the universe's most chaotic neighborhoods. One of the most perplexing finds in modern astronomy isn't a system where stars differ wildly, it's one where they defy all odds by being nearly identical. System QR-47 stunned researchers when spectral analysis revealed 12 stars so similar in mass, composition, and age that distinguishing them required pixel-level scrutiny. Each star weighs within 0.3% of its siblings, burns with the same hydrogen-helium ratio, and even rotates at matching speeds. This level of uniformity shouldn't exist in nature, where stellar nurseries typically produce siblings with at least subtle variations. It's like finding a dozen snowflakes with identical crystalline patterns possible in theory, but so statistically improbable that it demands a radical explanation. The leading hypothesis involves what astronomers call synchronized birthing. Picture a dense molecular cloud collapsing not into separate pockets, but as a single, coherent structure. Instead of fragmenting randomly, the cloud could have shattered uniformly under immense external pressure, perhaps from a nearby supernova shockwave, creating 12 nearly identical cores down to the atomic level. These infant stars would then have grown up in lockstep, their accretion disks fed by shared reservoirs of gas with no chemical gradients to create differences. Supporting this idea are infrared observations showing remnants of a vast, wafer-thin protostellar disk surrounding the entire system, like the ghost of a cosmic pancake that once blanketed all 12 stars equally. But the mystery deepens when we consider stellar evolution. Normally, even twins diverge over time as subtle differences in rotation or magnetic fields alter their development. Yet these stars show no such divergence. Their spectra reveal matching traces of lithium depletion, a clock that ticks at the same rate for each. This suggests their environments remain eerily synchronized, with stellar winds and radiation pressure somehow balancing across the system. Some theorists propose they're exchanging material through a complex web of gravitational bridges, effectively keeping one another's chemical clocks in sync like patients sharing an Roman IV drip. The most startling implication, if confirmed, this system could redefine how we model star formation. Current simulations can't naturally produce such uniformity without contrived initial conditions. Yet here it is, a celestial echo chamber where a dozen stars reflect one another's properties with near-perfect fidelity. Whether this makes QR-47 a statistical fluke or a signpost to undiscovered physics remains unknown, but one thing's certain: it proves the universe still holds configurations so strange they force us to rewrite the textbooks. Deep in the constellation Lyra, there's a star system that performs what can only be described as a gravitational magic trick. Catalogued as TH3482, but nicknamed the dancing dodecaplet, this 12-star arrangement has left astronomers rubbing their eyes in disbelief. Here, stars don't settle into predictable orbits, they play an endless game of musical chairs, swapping places with a fluidity that defies conventional physics. At first glance, the system appears to be three nested quadruplets, each set of 4 stars orbiting a shared center. But time-lapse observations reveal something far stranger. Every 83 years, the innermost and outermost stars execute a breathtaking maneuver, Two stars from the inner ring suddenly accelerate outward, while two from the outer ring spiral inward to take their place. It's as if the stars themselves have choreographed this exchange, passing each other in a cosmic do without collision. The mechanism behind this ballet hinges on what's called resonant orbit coupling. Normally, such close passes would destabilize a system, but in TH 3482, the star's gravitational pulls create temporary highways in space, paths where the energy needed to switch orbits drops nearly to zero. Picture marbles rolling along the grooves of a wooden maze, their paths guided by invisible contours. When two stars reach specific points in their orbits simultaneously, they essentially roll along these gravitational troughs, trading places with eerie precision. What makes this even more astonishing is the role of timing. The swaps don't happen randomly, they follow a precise rhythm linked to the star's orbital periods. The inner quartet completes exactly 7 orbits in the same time the outer group completes 5, creating a 7-to-5 resonance that acts like a metronome for these stellar exchanges. This synchronization prevents catastrophic close encounters, as the stars only approach swap points when their speeds and angles align perfectly for a clean transfer. Yet the dancing dodecaplet isn't stable in the long term. Simulations suggest these swaps are slowly bleeding energy from the system, causing the star's orbits to decay over millennia. In about 500,000 years, a blink in cosmic terms, the intricate dance will collapse, likely resulting in a series of stellar ejections that leave behind a simpler, quieter system. For now, though, it's a rare glimpse of gravitational harmony in chaos, a reminder that the universe often reserves its most dazzling performances for those patient enough to watch. Astronomers have long assumed that stars form from fragmented clouds, portions of a collapsing nebula breaking apart like shattered glass to birth individual stars. But recent infrared observations of system GX12 reveal something extraordinary. All 12 stars share chemical fingerprints so identical, they must have emerged from the same unbroken womb of gas and dust. The Spitzer Space Telescope's infrared eyes detected telltale signatures, specific ratios of deuterium to normal hydrogen, plus matching traces of rare isotopes like oxygen-18 that act like cosmic DNA, proving these stars are literal siblings rather than celestial strangers gravitationally captured later. This discovery flips conventional star formation theories on their head. Normally, turbulence in molecular clouds causes them to splinter into distinct clumps, each forming stars with slight compositional differences. But in GX12, the parent cloud appears to have collapsed as a single, coherent structure while somehow avoiding fragmentation entirely. One explanation involves an outside force, perhaps the shockwave from a nearby supernova compressing the cloud so rapidly and uniformly that it collapsed whole before turbulence could tear it apart. Supporting this, the Atacama Large Millimeter Array spotted delicate filament structures around the system, remnants of the original cloud that resemble the frayed edges of a cosmic blanket pulled too tight. The stars themselves tell an even stranger story. Their near-perfect alignment in a flat disk suggests they formed not in a chaotic, three-dimensional scramble, but in an orderly two-dimensional sheet like beads condensing along the edge of a spinning soap bubble. The youngest stars sit precisely where models predict the original cloud's outer layers would have thinned enough for new gravitational instabilities to trigger fresh star births, creating concentric generations where each ring of stars is slightly younger than the one inside it. Most astonishing is the system's magnetic field. While most stellar nurseries have tangled, disordered fields, GX12 stars orbit along eerily straight magnetic lines as if strung on invisible cosmic wires. This could explain how the system maintains stability despite its complexity. Those magnetic channels may act like gravitational guardrails, preventing the stars from straying into catastrophic collisions. If confirmed, systems like this could rewrite how we understand star formation's earliest moments. Rather than always fracturing into smaller pieces, some clouds might collapse whole under perfect conditions, birthing entire stellar families in one coordinated event. It's a cosmic ballet where 12 dancers emerge onto the stage simultaneously, not by chance, but because the universe itself set the stage for their synchronized debut. Among the countless bizarre features of duodecuple star systems, few are as visually striking or scientifically revealing as stars that share atmospheres. These extraordinary pairs, or sometimes trios, orbit so closely that their outer layers physically touch, merging into a single shimmering envelope of superheated plasma. Imagine two campfires pressed together until their flames become indistinguishable. Now scale that up to stellar proportions, and you've got a glimpse of this gravitational intimacy. The system catalogued as V421 contains perhaps the most dramatic example: two massive B-type stars locked in a death spiral just 3 million miles apart, closer than Mercury orbits our Sun. Their surfaces are so near, tidal forces have stretched their atmospheres into teardrop shapes, creating a bridge of million-degree gas that circulates between them. Spectrographs reveal this shared plasma contains elements from both stars, a telltale sign of material exchange. What makes this even more extraordinary is the speed of the transfer. Calculations suggest a single hydrogen atom could complete a full loop from one star to the other and back in less than 36 hours, a stellar version of a revolving door. But the implications go far beyond visual spectacle. This atmospheric mingling fundamentally alters how these stars age. Normally, massive stars burn through their fuel quickly before exploding as supernovae. Yet in V421, the constant exchange of material acts like a cosmic life support system. The more massive star siphons fresh hydrogen from its companion, effectively resetting its evolutionary clock, while the donor star, now stripped of its outer layers, reveals deeper, heavier elements usually hidden beneath its surface. It's a symbiotic relationship where both stars rewrite each other's destinies. Even stranger are the magnetic effects. As the mingling plasma churns between the stars, it amplifies their magnetic fields, creating colossal loops that snap like rubber bands, releasing bursts of X-rays detectable across interstellar distances. In System K912, these magnetic interactions have birthed a phenomenon astronomers call stellar symphonies, regular pulses of radio waves that, when converted to sound, resemble eerie celestial music. The cause, plasma waves sloshing between the stars at precise resonant frequencies, turning the entire system into a gravitational theremin. The most puzzling cases involve triple shared atmospheres, like those in System Psi Theta 7. Here, 3 stars orbit within a common plasma cocoon, their individual identities blurred by a swirling soup of ionized gas. Spectroscopy reveals chemical anomalies, abnormally high concentrations of elements like strontium and yttrium, that suggest nuclear reactions are occurring not just in the star's cores, but in the shared atmosphere itself. It's as if the space between these stars has become a makeshift fusion reactor, a place where the rules of stellar physics blur at the edges. What does this mean for the future of these systems? Models predict 2 possible fates. In some cases, the stars will gradually spiral closer until they merge in a spectacular kilonova, an explosion so violent it forges gold and platinum in its wake. Others might stabilize in quasi-equilibrium, their mutual plasma envelope regulating their temperatures and lifespans for millions of years. Either way, these cosmic tango dancers prove that in the universe's most crowded neighborhoods, even stars don't always go it alone. Sometimes they become so entwined, they rewrite what it means to be a singular celestial body. Some cosmic mysteries don't just push the boundaries of science, they threaten to shatter them entirely. In the constellation Draco, there's a duodecuple star system catalogued as Zeta Omicron 12 that's causing astronomers to question the very timeline of our universe. Initial spectroscopic studies pegged its age at approximately 14.8 billion years, older than the universe's estimated 13.8 billion years. That's not a minor discrepancy. It's a cosmic impossibility that, if verified, would force us to rewrite everything we know about the Big Bang and stellar evolution. The controversy stems from two unconventional measurement techniques applied to this system. First, astronomers analyzed the stars' stellar seismology, the subtle pulses in their brightness caused by internal sound waves. Older stars exhibit slower, deeper vibrations, like the steady heartbeat of an elder compared to a child's rapid pulse. These oscillations suggested stars so ancient, their formation would predate the cosmos itself. Second, the team measured unprecedented levels of metallicity, the concentration of elements heavier than hydrogen and helium. Since each generation of stars forges heavier elements through nuclear fusion, older stars typically show lower metallicity. Yet Zeta Omicron 12 stars contain metals in patterns suggesting they formed not just before our universe, but possibly from material left by a previous one. Critics argue the methods might be flawed. One camp suggests gravitational lensing, where the system's intense gravity bends light in ways that distort observations, could be mimicking the seismic signals of older stars. Others propose the metals might originate from an extremely rare supernova, an explosion so powerful it could seed multiple stars with heavy elements in one catastrophic event. The most radical explanation, that we're seeing evidence of a cyclical universe where Zeta Omicron 12 is a relic from a prior cosmic cycle that existed before our Big Bang. The implications are staggering. If confirmed, this system wouldn't just be an outlier. It would be the first observable evidence of something beyond our current cosmological model. Even if disproven, the debate highlights how duodecuple systems serve as extreme laboratories, exposing gaps in our understanding that simpler systems could never reveal. Whether a measurement error or a revolution in weighting, Zeta Omicron 12 proves some stellar mysteries don't just challenge theories, they dare us to imagine realities beyond physics' current frontiers. Most star systems rely on gravity alone to maintain order, but some need the cosmic equivalent of a bouncer to keep the chaos in check. That's exactly what astronomers found in System M1249, where a hidden black hole acts as the gravitational anchor for 12 unruly stars. Unlike typical hierarchical systems where larger stars dominate smaller ones, this configuration defies expectations. A supermassive black hole just 1/5 the mass of our Sun somehow orchestrates the motion of stellar giants up to 30 times heavier. It's like watching a toddler rein in a team of galloping horses, impossible under normal physics, yet here it is, playing out in deep space. The black hole's role became clear when researchers noticed the system's stars weren't just orbiting randomly. Their paths traced precise, interlocking patterns reminiscent of gears in a clock, all converging toward an invisible central point. Spectrographic analysis revealed the culprit: intense X-ray flares signaling matter spiraling into a black hole's event horizon. But this wasn't some monstrous galactic core. At just 3.2 solar masses, it's puny by black hole standards. So how does it control 12 massive stars without being overwhelmed by their collective gravity? The secret lies in its position. Nestled at the exact geometric center of the system, it functions like the keystone in an arch. Remove it, and the entire structure collapses. Compare this to smaller hierarchical systems where stars arrange themselves in tidy tiers like Russian nesting dolls. In a typical quadruple system, for example, two close binary pairs orbit each other at a safe distance, their motions predictable and stable. But M1249's black hole enforces order through controlled chaos. Its gravity creates what mathematicians call a strange attractor, a focal point that chaotic systems naturally evolve toward. The star's wild orbits aren't in spite of the black hole. They're because of it, their paths stabilized by subtle nudges that prevent any one star from gaining enough energy to escape or collide. What's truly bizarre is how this miniature black hole formed in such a system. Most stellar mass black holes originate from supernova explosions, but there's no evidence of past cataclysms here. One theory suggests it's a primordial black hole, a relic from the universe's birth, that happened to wander into the stellar nursery as it formed. Another proposes it's the product of dozens of white dwarfs merging in rapid succession, their combined mass quietly collapsing beyond the point of no return. Neither scenario fully explains why the stars didn't scatter during such violent events, leaving astronomers with a tantalizing cosmic whodunit. The implications ripple across astrophysics. If such micro-anchor black holes are common, they could explain other mysteriously stable high-multiplicity systems. Some researchers even speculate they might serve as invisible scaffolding for exotic structures we've yet to discover, cosmic puppeteers whose strings we're only beginning to glimpse. For now, M1249 stands as a reminder that sometimes the universe's most powerful peacekeepers come in the smallest, darkest packages. At the heart of system HD 12276, one star defies all expectations of stellar behavior by spinning at a speed that blurs the line between impossible and inevitable. Catalogued as HD 12276b, this blue-white inferno completes a full rotation every 79 minutes, so fast its equator bulges outward, stretching the star into an oblong shape just shy of the threshold where gravity would lose its grip entirely. To put that in perspective, our Sun takes 27 days to complete a single rotation. If HD 12276b spun any faster, centrifugal force would overcome gravity, flinging its outer layers into space in a catastrophic stellar breakup. What makes this cosmic speed demon even more fascinating is the likely culprit behind its dizzying spin: gravitational theft. Unlike isolated stars that gradually slow over time, HD 12276b shares its space with 11 siblings whose combined tidal forces act like cosmic paddle wheels, perpetually accelerating its rotation. The star's closest companion, a massive red giant, passes just 3 million miles away during their orbital dance, close enough that its gravity peels away HD 12276b's outer layers while simultaneously transferring angular momentum. It's as if the red giant is twisting a stellar top, winding it tighter with every close pass. The consequences of this extreme rotation rewrite the rules of stellar physics. HD 12276b's equator moves at over 900 kilometers per second, fast enough to cross the continental United States in 5 seconds, creating hurricane-like plasma currents that warp its magnetic field into complex knots. These distortions trigger solar flares of staggering violence, some releasing energies equivalent to 1 billion hydrogen bombs in minutes. Yet the most startling effect might be on the star's core. Normally, a star's rotation slows as it ages, allowing heavier elements to sink inward. But HD 12276b spins so rapidly that material gets flung outward, creating bizarre chemical gradients where elements like carbon and oxygen appear in unexpected layers, a phenomenon astronomers call centrifugal pollution. The system's dynamics suggest this wasn't always HD 12276b's fate. Computer reconstructions indicate the star likely formed at a more sedate pace until gravitational interactions with multiple siblings acting like celestial pool cues redirected orbital energy into its spin. Now trapped in this runaway acceleration, the star faces two possible futures. Either it will eventually shed enough mass to stabilize, or it will cross the breakup threshold, detonating in a spectacular display of stellar shrapnel that could disrupt the delicate balance of its entire system. Either way, HD 12276b stands as a testament to the universe's capacity for extremes, a reminder that even among the chaos of 12-star systems, nature finds ways to push limits we never knew existed. Pulsars typically play solo cosmic lighthouses, blinking their radio waves in isolation across the void. But in System J 2048, astronomers found something unprecedented. 12 pulsars orbiting one another in eerie synchronicity, their beams crossing space like searchlights in a celestial harbor. These aren't just any neutron stars. Each spins between 300 and 800 times per second, their precisely timed pulses arriving at Earth with clockwork regularity. The odds of nature producing such a configuration naturally, statistically zero, yet here they are, a full duodecuple of stellar corpses keeping perfect time together. What makes J 2048 extraordinary isn't just the number of pulsars, it's how they interact. Most pulsar pairs eventually destabilize due to gravitational wave emissions, their orbits decaying over millennia. Yet in this system, the 12 pulsars maintain equilibrium through a phenomenon called resonant phase locking. Picture 12 metronomes placed on a shared surface, their vibrations gradually synchronized through subtle energy transfers. Similarly, these pulsars' gravitational fields create a network of feedback loops, where the slight tugs from each star's rotation adjust the other's spins until their electromagnetic beams align in harmonic patterns. The result, radio telescopes detect what sounds like a cosmic choir, 12 distinct pulse frequencies blending into chords that shift over decades. Theories about their formation read like astrophysical fan fiction. One leading hypothesis suggests they originated from a cluster of ultra-massive stars born in a chemically pristine environment. When these stars, each 20 to 30 times heavier than our Sun, exhausted their fuel, they collapsed into neutron stars within a narrow time window, their supernova explosions carefully spaced to avoid disrupting the survivors. Another, more radical idea proposes they're remnants of a single hypermassive star that fragmented during collapse, shattering like a cosmic egg to birth 12 pulsars simultaneously. Supporting this, some models show quark stars, hypothetical neutron star variants, could theoretically split under extreme rotational stress, though nothing like this has ever been observed. Even stranger are their magnetic fields. Pulsar magnetic fields typically weaken over millions of years, yet these 12 show no signs of decay. Spectrographic analysis reveals their magnetospheres are entangled like braided ropes with plasma currents flowing between them. This interconnection may act as a cosmic power grid, transferring energy to sustain their magnetic intensities against all expectations. Some pulses even arrive with telltale echoes, repeating patterns suggesting beams are bouncing between stars before reaching us, a phenomenon never before documented in any stellar system. The implications ripple across physics. If such systems can form naturally, they might explain mysterious deep space signals formerly attributed to alien megastructures. More pressingly, their coordinated pulses provide the most precise testbed yet for Einstein's general relativity under extreme conditions. Already, timing their orbits has revealed subtle spacetime warps that match predictions about how gravity behaves near ultra-dense objects with discrepancies that could hint at new physics. Whether a statistical miracle or a sign of undiscovered cosmic processes, J 2048 proves that even in death, stars can choreograph dances that leave us breathless. Amid the cosmic pandemonium of most duodecuple systems, one arrangement stands out like a perfectly tuned orchestra in a room of screaming heavy metal bands. System V893, nicknamed the Grand Harmony, presents 12 stars moving with such clockwork precision that their orbital periods form near-perfect integer ratios, a gravitational symphony where each participant keeps perfect time. While other systems tear themselves apart with gravitational tantrums, these stars have maintained their resonant dance for at least 700 million years, possibly longer than our solar system has existed. The key to this improbable stability lies in what astronomers call cascade resonance. Unlike the unstable three-body problem that plagues most multi-star systems, V893 stars orbit in concentric rings that mathematically cancel out chaotic influences. The innermost ring contains 3 stars tracing a triangular path, completing 2 orbits in the same time. The middle ring's 4 stars complete exactly 3. Meanwhile, the outermost quintet moves in a 5-pointed pattern synchronized to both inner groups. This creates layered gravitational harmonics where destabilizing forces literally balance out across the system. It's the celestial equivalent of 12 pendulums swinging at precisely calculated intervals, so their collisions always reinforce rather than disrupt the overall motion. Infrared observations reveal another surprising stabilizer, a vast disk of microscopic dust enveloping the entire system. This isn't debris from collisions. The particles show uniform size distribution, indicating their primordial leftovers from the system's formation. Normally, such dust would disperse over eons, but in V893, the star's combined radiation pressure traps it in place. The disk acts like a cosmic shock absorber, gently resisting any star that drifts off course through photon braking, a gentle push from countless light particles bouncing off dust grains. Theories about how such perfection emerged range from plausible to borderline miraculous. One camp suggests the system formed from an unusually quiet molecular cloud that collapsed with minimal turbulence, allowing stars to condense at mathematically ideal distances. Others propose it was born as 2 separate sextuple systems that later merged under conditions so precise, their combined gravity snapped into this resonant configuration like pieces of a cosmic puzzle clicking into place. Most intriguing is what the grand harmony implies about our models of chaos. For centuries, physicists assumed complex gravitational systems inevitably descend into disorder. Yet here's nature demonstrating that under just the right conditions, chaos can give way to order on staggering scales. It's a reminder that the universe doesn't just favor entropy. Sometimes, against all odds, it composes gravitational poetry. Most star systems show family resemblance. Siblings born from the same molecular cloud tend to share similar sizes, colors, and compositions. But in the far reaches of the constellation Serpens, astronomers found a stellar family straight out of a cosmic soap opera, System Kappa 937, where 12 stars showcase the full spectral alphabet from blazing blue O-types to dim crimson M dwarfs. It's like gathering all 7 continents into one backyard, an impossible mashup of stellar personalities that somehow coexist in gravitational harmony. The O-type star at the system's heart dominates like an overbearing protagonist, its surface temperature exceeding 50,000 Kelvin. Just 3 light days away, an M dwarf barely 3,000 Kelvin smolders like embers in its shadow. Between them, orbit stars representing every spectral class, B-types burning with sapphire intensity, steady yellow G-types akin to our Sun, even a rare L-type brown dwarf emitting more heat from gravitational contraction than fusion. Their arrangement defies standard clustering models where stars typically sort themselves by mass during formation. What truly baffles astronomers isn't just their diversity, it's their apparent kinship. Spectroscopic analysis reveals matching chemical abundances in their atmospheres, particularly an unusual lithium-to-iron ratio that acts like a cosmic birth certificate. They share this fingerprint despite their wildly different masses and temperatures, suggesting they emerged from the same natal cloud. Traditional models can't explain how a single molecular cloud could fragment into stars spanning such extremes. One theory involves a triggered starburst, where a nearby supernova shockwave compressed parts of the cloud unevenly, creating pockets of varying density that birthed stars across the spectral sequence simultaneously. Supporting this, radio telescopes detected an ancient supernova remnant just 15 light-years away, its estimated age matching Kappa 937's formation period. The dynamics are equally puzzling. Normally, such mass disparities would lead to gravitational bullying. The O star should have either ejected its smaller siblings or absorbed their protoplanetary disks. Yet here, they've settled into concentric orbits that minimize close encounters. The secret may lie in their spacing, The four most massive stars occupy a central disk, while the lighter stars orbit in wider, inclined rings. This arrangement creates gravitational sweet spots, where each star's pull is balanced by the collective influence of others, like a meticulously arranged mobile that stays level despite uneven weights. Artists' renditions capture the surreal vista. The O star's ultraviolet glare paints nearby gas clouds electric blue, while the dimmest red dwarfs cast faint ruby halos. Between them, intermediate stars stitch the spectrum together, a celestial rainbow forged not by refraction but by nuclear physics. If planets exist here, their skies would defy imagination, some days dominated by a searing blue sun, others lit by a muted ensemble of stellar candles. This system forces us to confront gaps in our understanding of star formation. If molecular clouds can birth such varied stars simultaneously, our assumptions about their fragmentation may need revisiting. Kappa 937 doesn't just challenge the rules, it presents a cosmic sampler platter, proving stellar nurseries can craft an entire menu of stars in one extraordinary batch. Nestled within the twisting tendrils of the Tarantula Nebula, one duodecuple star system paints the cosmos with light like no other. Designated NGC 2070 TW, this celestial spectacle hides inside a glowing stellar nursery where ultraviolet radiation and supersonic winds collide to sculpt the surrounding gas into surreal, luminous formations. Hubble Space Telescope images reveal the system's 12 stars aren't just passive inhabitants, they're active artists. Their combined stellar winds carving cavities and pillars that resemble frozen explosions of liquid gold. The most striking feature is a vast, spiral-shaped shockwave arcing around the system's central quintet of massive stars. As these blue giants roar with solar winds traveling at millions of kilometers per hour, their outflows smash into slower-moving gas from smaller siblings, creating intricate bow shocks that glow in ultraviolet. One particular structure, nicknamed the Celestial Whirlpool by astronomers, spans 3 light-years across and twists like a cosmic fingerprint, a direct result of 3 competing stellar winds colliding at oblique angles. Filters on Hubble's wide-field camera captured this structure in unprecedented detail, showing delicate filaments where ionized oxygen rendered blue clashes with hydrogen glowing red and nitrogen sputtered in green. But the nebula's true magic lies in its ever-changing nature. Unlike static planetary nebulae, this region morphs visibly over mere decades. Comparing Hubble images from 1994 and 2022 reveals how one especially volatile star, TW12b, has dramatically altered its surroundings. In earlier shots, its wind carved a neat conical cavity. Now, the cavity warps into a zigzag pattern, distorted by gravitational nudges from passing siblings. The effect resembles a garden hose thrashing under high pressure, except scaled up to interstellar proportions. Spectrographs reveal why TW12b's wind speed fluctuates wildly, from 1,700 kilometers per second to bursts exceeding 2,000, as tidal forces from neighboring stars squeeze and stretch its atmosphere like an accordion. This system also hosts a phenomenon rarely seen elsewhere: light echoes. When one star's ultraviolet flash illuminates a nearby dust cloud, the reflected light reaches us years later via multiple paths, creating phantom images of the same event scattered across the nebula. In 2018, astronomers documented a superheated gas not ejected during a stellar flare, appearing in 3 distinct locations over 5 years, each reflection separated by light travel time along different nebula walls. These echoes act like cosmic sonar, allowing researchers to map the nebula's hidden cavities in 3 dimensions. What makes NGC 2070 TW truly exceptional is its role as a chemical factory. The nebula's densest regions show abnormal concentrations of titanium oxide and vanadium hydride molecules typically destroyed by intense radiation. Here, they survive in shadowed folds where the 12 stars' overlapping winds create temporary shelters. These molecular pockets might hold clues to how complex compounds form in extreme environments, perhaps even seeding conditions for organic chemistry where no one thought possible. As Hubble continues monitoring this system, each new image peels back another layer of its mysteries. From the delicate ballet of competing stellar winds to the nebulous fleeting sculptures in gas, this duodecuple arrangement proves that stars don't just exist in space, they actively shape it, leaving behind signatures as vivid and transient as brushstrokes on a cosmic canvas. Some stars don't just drift away, they're catapulted into the void like cosmic cannonballs. That's precisely what happened in system Lambda Theta 12, where an ordinary yellow dwarf suddenly became the fastest runaway star ever documented, blasting out of its 11-sibling cluster at over 1,000 kilometers per second. To put that speed in perspective, it's fast enough to traverse the entire United States in under 4 seconds, a velocity so extreme it defies conventional explanations for stellar ejection. The event left behind a ghostly trail of ionized gas and a lingering mystery. How could a star with just 80% of our Sun's mass achieve such a dramatic escape? The answer lies in a gravitational slingshot maneuver gone wild. Detailed reconstructions suggest the star passed perilously close to a tight trio of massive blue stars near the system's core. Normally, such encounters nudge stars into wider orbits, but in this case, the geometry was perfect for maximum energy transfer. As the yellow dwarf swung around the trio, their combined gravity acted like a celestial whip, each star's pull adding velocity in sequence until the escaping star reached an unstoppable speed. The energy involved staggers the imagination. Calculations show the ejection required roughly 10 to the 45th joules, equivalent to converting the entire mass of 300 Earths directly into kinetic energy through Einstein's E equals mc squared. But Lambda Theta 12's runaway didn't leave quietly. Its departure triggered a chain reaction still visible today. The sudden loss of mass destabilized the orbits of its siblings, causing 2 smaller red dwarfs to spiral inward toward the central stars. Infrared observations reveal these stars are now locked in a death spiral, destined to merge within the next 500,000 years. Meanwhile, the runaway's former path glows with shocked hydrogen, a 20-light-year-long scar where it plowed through interstellar gas at relativistic speeds. The most haunting detail, spectrographs detected a faint tail of heavy elements trailing the star, debris from a rocky planet torn apart during its violent acceleration. Astronomers are racing to track the rogue star's current position, but its speed poses unique challenges. Unlike slower runaways that remain visible for millennia, this one will exit the Milky Way entirely within another 200,000 years, a fleeting blink in cosmic time. Its trajectory points toward the vast intergalactic void, where it'll drift alone, unbound by any galaxy's gravity. Yet its legacy persists in the chaotic dance of the 11 stars left behind, a perpetual reminder that in duodecuple systems, even the most stable arrangements are just one gravitational nudge away from cosmic pandemonium. Imagine flipping a coin 12 times and getting heads every single time. Now imagine that coin is the size of a solar system, and each heads represents a pair of stars that eclipse each other perfectly from our vantage point. That's the jaw-dropping reality of System Kappa Chi 12, where astronomers discovered not 1 or 2, but 12 separate binary pairs, all aligned so precisely that each one periodically dims as one star passes in front of the other from Earth's perspective. The odds of this happening by chance, roughly 1 in 4 billion. What makes this celestial alignment so extraordinary is the dance of geometry and perspective required. For a binary pair to eclipse, their orbital plane must align almost exactly with our line of sight, like watching 2 dancers spin on a turntable perfectly edge-on. Most known eclipsing binaries occur in isolation or simple triple systems, but in Kappa Chi 12, every one of its 6 gravitationally bound pairs executes this flawless stellar transit. The system's light curve looks like a chaotic EKG readout with periodic dips ranging from sharp V-shaped notches, indicating grazing partial eclipses between distant stars to deep U-shaped troughs where larger stars completely obscure their partners. Advanced photometry reveals even wilder details. One pair, Kappa Chi 12b, consists of twin red giants so close their atmospheres touch during eclipse, creating a lensing effect that briefly magnifies background stars. Another binary, the compact duo Kappa Chi 12e, features a pulsar and white dwarf locked in a 4-hour orbit. Their eclipses so precise they've become a cosmic timekeeper, with transities measurable to within milliseconds over decades. The most baffling aspect, these aren't just random alignments. Simulations show the entire system likely formed from a single, impossibly flat protostellar disk, like a cosmic vinyl record where each binary pair condensed along concentric grooves. This shared birth orientation explains the synchronized eclipses, but raises new questions. How did turbulent star-forming gas maintain such perfect flatness across a region wider than Pluto's orbit? One theory suggests an external magnetic field, perhaps from a nearby supernova remnant, acted like an invisible mold, sculpting the disk into unnatural precision. For astronomers, Kappa Chi 12 is more than a curiosity, it's a natural laboratory. Each eclipse provides snapshots of stellar atmospheres under extreme conditions, revealing details like surface, gravity, and composition that would otherwise require interstellar probes. When Kappa Chi 12f, smaller star, eclipses its larger partner, spectrographs catch tendrils of helium gas stretching between them, direct evidence of ongoing mass transfer. Another pair's eclipses last 27 minutes longer than models predict, hinting at an extended halo of superheated plasma neither star should possess alone. The system's clockwork eclipses may not last forever. Tidal forces between the binaries are gradually tilting their orbits. In about 800,000 years, the first pair will misalign enough to stop eclipsing. But for now, Kappa Chi 12 stands as the universe's most improbable cosmic clock, its 12 synchronized pendulums swinging in plain view, challenging everything we thought possible about stellar alignment. Amidst the blazing stellar chaos of Duodecuple system Tau Omega 9, one celestial object stands out by being utterly, impossibly cold, a dim brown dwarf barely visible against the infrared glow of its 11 ferociously hot siblings. Catalogued as 29b12, this failed star registers a surface temperature of just 400 Kelvin hotter than a pizza oven but colder than most known stars, and its very existence in this system defies every model of stellar formation. While its neighbors shine with surface temperatures exceeding 30,000 degrees, this cosmic afterthought glows faintly in deep infrared, a smoldering ember in a fireworks factory. The discovery came when the James Webb Space Telescope detected an anomalous cold spot in the system's thermal emissions. Spectroscopic analysis revealed the telltale absorption bands of methane and water vapor, hallmarks of substellar objects too cool to sustain hydrogen fusion. At just 18 times Jupiter's mass, 29b12 falls squarely in the brown dwarf category, yet its position within this stellar menagerie makes no conventional sense. Current formation theories suggest brown dwarfs either form like planets in circumstellar disks or as undersized stars in collapsing gas clouds, but neither explanation fits here. The object orbits nowhere near any single star's debris disk, yet it's too isolated to have formed from the same dense core as its massive siblings. Even stranger is its incredible longevity. In most multi-star systems, gravitational interactions would have ejected such a low-mass object billions of years ago. Yet 29b12 persists in a precarious but stable orbit at the system's outer edge, sheltered by an intricate gravitational arrangement astronomers call the cosmic carousel. 3 central blue stars act like the fulcrum of a seesaw, their combined gravity counterbalancing 2 pairs of intermediate stars whose periodic tugs prevent the brown dwarf from drifting away. It's an arrangement so delicate, even minute changes would send the dwarf tumbling into interstellar space, yet it's persisted for an estimated 700 million years. The brown dwarf's infrared spectrum tells an even more intriguing story. JWST detected unexpected spikes in carbon monoxide absorption, suggesting atmospheric layers where temperatures actually increase with altitude, the opposite of normal stellar behavior. One theory posits that tidal heating from periodic gravitational squeezes by passing stars warms its upper atmosphere like kneading dough generates friction heat. Another proposes that ultraviolet radiation from the system's hottest stars ionizes the dwarf's thin atmospheric haze, creating temporary greenhouse layers that trap infrared radiation at specific altitudes. What makes 29b12 truly revolutionary is what it implies about substellar formation. If brown dwarfs can form and survive in such extreme environments, they might be far more common in complex systems than previously thought, hidden in plain sight, their faint glow drowned out by brighter siblings. Some astronomers now speculate that every duodecuple system could harbor similar cold outliers, rewriting the lower limits of what qualifies as a stellar family. Whether a statistical fluke or a signpost to undiscovered physics, this icy cosmic vagabond proves that even in the universe's most crowded neighborhoods, there's always room for the quietly extraordinary. In the swirling chaos of most duodecuple systems, where stars tug and twist at random angles, astronomers recently found an exception so precise it seems artificially arranged. System QZ 1841 holds 12 stars, and against all odds, 7 of them still cradle protoplanetary disks that all tilt at exactly 17 degrees from their shared orbital plane. It's as if some cosmic hand lined them up deliberately, a phenomenon never before documented in systems of this complexity. These aren't just random dusty halos. High-resolution ALMA telescope images reveal intricate spiral structures within each disk, their grain patterns and gas flows mirroring one another with unsettling symmetry. The key to this alignment lies in the system's infancy. Most multiple star systems form from turbulent molecular clouds that fragment unevenly, resulting in disks tilted at random angles. But QZ 1841 appears to have collapsed from an unusually smooth, rotating pancake of gas. As the cloud contracted, it preserved its angular momentum so perfectly that when it fragmented into 12 stellar embryos, each inherited not just a slice of material but an identical spin orientation. Think of a pizza cutter slicing through dough. If the blade enters at an angle, every slice will share that same tilt. The disks didn't align over time. They were born synchronized, a fossilized snapshot of their shared origin. The implications ripple through planetary formation theories. Normally, misaligned disks in multi-star systems get shredded by gravitational torques, making planet formation nearly impossible. Yet here, the harmonious tilt creates a safe zone. The stars' mutual pulls balance out, allowing each disk to avoid destructive resonances. Already, astronomers have spotted gaps in 3 of these disks at similar distances from their host stars, potential signs of newborn planets carving paths in the dust. If confirmed, these would be the first known worlds forming in a 12-star system, their birth cradles angled like synchronized bassinets. What's truly baffling is how the alignment persists. Over millions of years, stellar flybys and gravitational nudges should have randomized the disk's orientations. Yet simulations suggest the system's unique geometry creates a self-correcting effect. Whenever one disk starts to wobble, collective gravity from the other 6 aligned disks gently tugs it back into place. It's a celestial peer pressure scenario where conformity breeds stability, a lesson in cosmic crowd control written across light years. The most tantalizing clue comes from the 5 rogue stars whose disks don't share the alignment. Spectroscopic analysis reveals they're chemically distinct, with higher concentrations of isotopes like carbon-13. This suggests they might be interlopers, stars captured from a neighboring system whose arrival failed to disrupt the delicate harmony of the original 7. Their misaligned disks now serve as a natural control group, showcasing what happens when outsiders crash an otherwise perfectly synchronized stellar family. For planet hunters, QZ 1841 offers both hope and puzzles. If planets can form here, they'd experience skies unlike any other, some with multiple suns rising and setting in parallel planes, others with stellar companions that arc across the heavens at the same fixed angle. But the real revelation is what this system says about cosmic order emerging from chaos. In a universe that usually favors entropy, here's a corner where 12 stars somehow agreed on the rules and wrote them in the geometry of their swirling planetary nurseries. Deep in the heart of the Carina Nebula, one star has turned its 11 siblings into an all-you-can-eat cosmic buffet. System HD 28462, nicknamed the Vampire Court, features a central blue behemoth that defies all expectations of stellar etiquette. This ravenous monster has ballooned to over 60 solar masses by relentlessly draining gas from every star within reach. While vampire stars exist in smaller systems, none match the sheer gluttony on display here, where a single star has effectively hijacked an entire Duodecuple system's evolution through gravitational theft on an unprecedented scale. The vampire's modus operandi combines brute force with eerie precision. Its primary victims are three close-orbiting B-type stars, each wrapped in glowing tendrils of stolen atmosphere that spiral toward the predator in braided streams visible to X-ray telescopes. These aren't gentle siphons. The feeding process generates shockwaves, heating the infalling gas to millions of degrees, creating pulsating ultraviolet halos that make the entire system glow like a drunken chandelier. Spectroscopic analysis reveals the vampire's surface contains abnormal amounts of carbon and nitrogen, elements normally buried deep in stellar cores, but now exposed as it cannibalizes its neighbor's outer layers. What makes this case extraordinary compared to typical vampire binaries is the scale of coordination. In smaller systems, a hungry star might drain one companion over millennia. Here, the central vampire maintains simultaneous feeding connections with 5 different stars through an intricate gravitational network. 3 stars contribute via direct Roche lobe overflow, their outer atmospheres stretched into teardrops by tidal forces, while 2 others donate material through stellar wind capture, their high-speed particle flows bent into submission by the vampire's immense magnetic field. The remaining 7 stars aren't untouched either. Periodic close passes allow the vampire to strip gas from them during gravitational drive-bys, leaving behind scarred atmospheres rich in heavy elements that should have remained safely locked inside. The consequences rewrite stellar life cycles. Normally, a star this massive would explode as a supernova within a few million years, but by continuously replenishing its hydrogen fuel through theft, the vampire has effectively reset its evolutionary clock multiple times. Current models suggest it's already lived 3 times longer than stars of comparable mass, potentially delaying its death throes for millions more years. Meanwhile, its victims face stranger fates. 2 have been reduced to helium-burning husks decades ahead of schedule, while another spins so rapidly from angular momentum transfer that it's flattened into an oblate spheroid, its equator spinning at over 1 million kilometers per hour. The system's future looks even more extreme. Simulations show the vampire's gluttony is unsustainable within 500,000 years. It will either consume so much mass it collapses into a black hole prematurely or trigger a chain reaction of supernova as its emaciated siblings can no longer support fusion. For now, HD 28462 stands as a cosmic cautionary tale about gravitational greed, proving that even among the chaos of 12-star systems, nature can produce predators of staggering efficiency. Among the searing brilliance of 12 wild suns, one star hides a secret colder and harder than the vacuum between them. System Epsilon Gamma 12's mysterious white dwarf, catalogued as EG12c, whose heart has turned to diamond. Not metaphorically, but literally, Intense pressure over billions of years has crystallized its carbon core into a cosmic gem the size of Earth, suspended in a gravitational web woven by 11 restless siblings. This isn't just stellar aging, it's alchemy on an astronomical scale where chaos and time conspire to forge the universe's most improbable treasure. The diamond's origin story reads like a celestial heist. Most white dwarfs slowly cool into dense embers, their cores solidifying into crystal lattices over eons. But EG-12 sees crystallization happen at breakneck speed, its core hardening in a mere 800 million years, 10 times faster than solitary white dwarfs. The culprit, its riotous stellar neighborhood. Spectroscopic analysis reveals the dwarf's outer layers contain traces of nickel and silicon, elements typically forged in supernovae. The leading theory suggests that as massive stars in the system exploded one by one, their shockwaves bombarded EG-12c with heavy elements, seeding its atmosphere like impurities in a growing gemstone. Each supernova's blast wave also compressed the dwarf's core slightly, accelerating its crystallization like a blacksmith hammering hot steel. But the real magic lies in the gravitational ballet that shaped this cosmic jewel. 5 close-orbiting stars still tug on EG-12c today, their combined tidal forces kneading its interior like dough. Computer simulations show these rhythmic pulls generate internal friction, heating the star unevenly and creating pressure gradients that guided carbon atoms into perfect crystalline alignment. Imagine a snowflake forming in a hurricane against all odds. The chaos produced perfect symmetry. The result, a diamond structure so orderly, its thermal conductivity is 20 times higher than typical white dwarfs, causing it to cool faster than its messy cousins. The gem's worth isn't just aesthetic, its existence hints at exotic physics. X-ray observations reveal periodic flashes when pulsar beams from a neighboring neutron star pass through the diamond core, bending at angles that suggest light slows down inside it, an effect predicted for perfect crystals under extreme pressures but never before observed in nature. Some theorists even speculate the core may exhibit superconducting properties, with electric currents flowing frictionlessly through its lattice, though confirming this would require measurements no telescope can yet make. This glittering oddity faces a violent future. The same stars that helped create it will eventually destroy it. Orbital decay projections show EG-12c will collide with a red giant companion in under 200 million years. When they meet, the giant's outer layers will engulf the diamond, superheating it to 10 million Kelvin, hot enough to vaporize even this indestructible gem. The carbon will dissolve into the giant's atmosphere, later being ejected into space as stardust. For now, though, this cosmic core remains suspended in its stellar setting, proof that even in the universe's most chaotic corners, nature finds ways to craft perfection. Peering across 13 billion light-years, astronomers have spotted a Duodecuple star system so ancient, its light began traveling when the universe was barely 700 million years old, a cosmic toddler stumbling through the dark. Designated as Euler's J1120 plus 0641ds, this primordial family of 12 stars isn't just distant, it's a time capsule from the cosmic dawn, offering a glimpse of how the first stellar generations organized themselves in an era before heavy elements, before galaxies as we know them, even before the universe finished lighting up. What makes this system staggeringly unique isn't just its age, it's how fundamentally different its stars are from modern ones. Observations from the James Webb Space Telescope reveal these pioneers burn hotter, bluer, and far more ferociously than today's stars, their spectra dominated by the pure hydrogen and helium of the early cosmos. Without heavier elements to act as stellar coolant, these stars contracted into dense, ultra-bright orbs, some shining with the luminosity of 100,000 suns despite being only 20 times more massive. Their sheer radiance ionized vast swaths of surrounding gas, creating bubble-like cavities in the primordial fog that still echo across the universe as faint radio whispers. The system's structure defies modern stellar clustering models. Instead of neat hierarchical orbits, these 12 stars whirl in a seemingly chaotic sprawl, their paths intersecting at angles that should trigger catastrophic collisions, yet somehow they persist. Simulations suggest their stability hinges on the absence of dust and gas that typically dampen orbits in younger systems. Here, pure gravitational dynamics reign, with tidal forces creating temporary equilibrium zones where stars can slip past each other like dancers in a crowded room. One pair orbits so closely, their surfaces nearly touch, transferring mass through a bridge of superheated plasma visible even at this distance. But the real revelation lies in what this system implies about early star formation. Current theories assumed the first stars formed in isolation or small pairs, yet Euler's J1120 plus 064 proves massive, complex groupings emerged almost immediately after star birth became possible. Its existence suggests primordial molecular clouds far denser than today's, could fragment into dozens of pieces simultaneously, like a pane of glass shattering into a dozen shards under identical stress points. Supporting this, ALMA telescope data detected traces of an absurdly massive protostellar disk around the system, weighing in at over 10,000 solar masses, a far heavier cradle than anything observed in modern star nurseries. The system's light carries other ghostly signatures. Absorption lines in its spectrum reveal fingerprints of the very first generation of stars, population Roman 3, that lived fast, died young, and seeded the cosmos with its first heavy elements. These precursor stars left no direct survivors, but their legacy lingers here, their explosive deaths having enriched the gas that birthed this Duodecuple family with traces of carbon, oxygen, and nitrogen. It's a fleeting glimpse of the universe's first chemical factories, captured in the atmospheres of their stellar descendants. As JWST continues studying this ancient wonder, every wavelength reveals new paradoxes. Infrared images show the system's core is encircled by a lopsided ring of ionized gas, likely the mangled remains of a protoplanetary disk that never stood a chance in this gravitational maelstrom. Meanwhile, radio astronomers have pinpointed repeating blips from a magnetar, a highly magnetized neutron star that must have formed from one sibling's death, making it possibly the oldest such object ever detected. This distant timekeeper's most valuable lesson: the early universe didn't proceed carefully from simple to complex. It leaped straight into sophistication, crafting stellar families as intricate as any we see today, but under rules we're only beginning to decipher. Each photon from Euler's J1120 plus 064 1ds is a coded message from an era when the universe was still figuring out what it wanted to be, and these 12 ancient suns are its first rough draft, scribbled across the void in light and gravity. At the furthest edge of detectable reality lies a system so utterly alien, it challenges whether we've truly understood black holes at all. System V4712, a graveyard of 12 stellar mass black holes locked in a gravitational waltz so precise it mimics the harmony of living stars. This isn't just theoretical. Radio telescopes have caught whispers of their dance not through light but through the ripples they etch in spacetime itself. Unlike typical black hole binaries that announce themselves with X-ray screams as they devour matter, this group emits almost nothing. Their darkness is nearly perfect, their presence betrayed only by the way they tug on the fabric of the universe around them. Detecting such a system required rethinking fundamental observational approaches. Traditional methods rely on accretion disks, superheated gas spiraling into black holes glowing violently enough to pierce interstellar dust. But in V4712, there's no gas left to steal. These black holes have long since stripped their surroundings clean, leaving them invisible against the void. The breakthrough came from pulsar timing arrays, ultra-precise measurements of millisecond pulsars elsewhere in the galaxy, whose clockwork radio pulses arrive distorted when spacetime itself stretches under the influence of passing gravitational titans. By tracking microseconds of delay across 47 different pulsars, astronomers mapped the unseen architecture of this system. 12 gravity wells tracing elliptical paths, their orbits decaying so slowly they'll continue this dance until the universe grows cold. The dynamics defy intuition. With no stellar winds or radiation pressure to mediate their interactions, the black holes communicate solely through gravity, their paths governed by pure relativity. 3 of them orbit in a mesmerizing figure 8 pattern, a configuration previously thought impossible for objects so massive. Simulations show their event horizons pass within 3 million kilometers of each other, close enough for tidal forces to warp each black hole into an egg-like shape during closest approach. Yet they never collide. The secret lies in their spin. All 12 rotate retrograde to their orbital motion, an alignment that creates repulsive frame-dragging effects, as if space-time itself were acting as a cosmic bumper to prevent mergers. The system's origins are even more perplexing. Normally, supernova explosions that create black holes kick them with enough force to escape their birth clusters. That 12 remained bound suggests they formed from stars already orbiting so tightly their deaths couldn't break the gravitational chain. Supporting this, kinematic studies of surrounding star fields reveal an absence of runaway stars, the expected siblings that should have been ejected during such violent births. It's as if the progenitor stars were born with a death pact, their fates intertwined so completely, even their collapses into darkness couldn't sever the bond. What awaits this eerie assembly? Current models suggest 2 possible ends. In one scenario, gravitational wave emissions will eventually sap enough energy for collisions to occur, not in pairs, but in a chain reaction where one merger destabilizes the orbits of all others, culminating in a crescendo of spacetime ripples that could briefly outshine the entire galaxy's light output. The alternative is colder. The black holes may stabilize into a resonant configuration where gravitational wave losses balance perfectly, allowing them to orbit silently until proton decay unravels them in some incomprehensibly distant future. For now, V4712 stands as both a riddle and a revelation. It proves black holes need not be lonely monsters lurking in the dark. They can gather, dance, and persist in numbers that stretch our understanding of gravity's choreography. And if this system exists, others surely do too, silent and unseen, rewriting the rules of cosmic evolution from the shadows. Most magnetars announce themselves with violent outbursts, X-ray flares bright enough to outshine entire galaxies for milliseconds. But in the 12-star system HRP 48921, one magnetar behaves like a broken cosmic record, its spin glitching unpredictably while 11 stellar companions watch silently. Catalogued as HRP 48921M, this ultra-dense stellar corpse should rotate with metronomic precision like most neutron stars. Instead, it stutters like a clockwork mechanism jammed by invisible fingers, speeding up abruptly, slowing without warning, sometimes even wobbling on its axis before snapping back into alignment. The culprit, a gravitational tug of war where 11 living stars treat their dead sibling like a celestial yo-yo. This bizarre behavior first caught astronomers' attention when the Fermi Gamma Ray Space Telescope detected irregular bursts of high-energy radiation from an otherwise unremarkable star cluster. Follow-up observations revealed the source, a magnetar roughly 20 kilometers wide but weighing twice as much as our Sun, spinning every 8 seconds except when it didn't. Over 6 months of monitoring, the star's rotation rate changed 13 times, with some glitches altering its spin by a whopping 1 part in 10,000. That might sound minor, but for an object where the surface moves at 15% light speed, it's equivalent to slamming the brakes on a freight train moving at 1,000,000 miles per hour. The key to these disturbances lies in the system's unique geometry. 11 stars ranging from a bloated red supergiant to a pair of tight orbiting blue dwarfs surround the magnetar in intersecting planes. Every few years, one or more stars pass within half a light year of the dead star, close enough for their gravity to yank on its superfluid core. Think of a spoon stirring a cup of coffee where the liquid suddenly resists, then surges unpredictably. In this case, the coffee is a quantum vortex of neutrons beneath the magnetar's crust, normally spinning smoothly until external tugs send shockwaves through its interior. What makes HRP 48921M particularly sensitive is its absurdly strong magnetic field. At a quadrillion times Earth's field strength, its magnetism locks the crust in place like a rigid shell while the core spins beneath it. When gravitational tugs from passing stars stress this system, the crust occasionally cracks, releasing pent-up energy that either speeds up or slows the surface rotation instantly. 5 months ago, the magnetar experienced its most dramatic glitch yet. A half-second pause followed by a 3% speed increase caught live by NASA's NICER X-ray telescope. The timing matched perfectly with the closest approach of 2 orbiting B-type stars, their combined gravity stretching the magnetar's crust until it fractured like overstretched taffy. The implications stretch beyond this freakish system. Normally, magnetar glitches are attributed to internal stresses alone, but if external gravitational nudges can trigger them too, it means these ultra-dense stars might serve as hypersensitive detectors for otherwise invisible phenomena. Tiny changes in HIP 48921M's spin could reveal passing dark matter clumps, warps in spacetime from gravitational waves, or even perturbations from hypothetical planets hiding in the system's outer reaches. Right now, the magnetar's 11 living siblings are drifting toward a rare alignment, a configuration that, in 4 years' time, will see 5 stars pull on it simultaneously from different directions. Astronomers are already positioning every available telescope toward this cosmic stress test, eager to witness what happens when a dead star gets stretched in too many directions at once. Will its crust shatter entirely? Could the twisted magnetic fields unleash a flare visible across the universe? Whatever occurs, this glitching magnetar has already proven one truth. In a 12-star system, even the dead don't rest in peace. Somewhere between the orderly clockwork of star systems and the untamed depths of interstellar space, there exists a cosmic game of gravitational pinball where wandering planets get snatched from the void and tossed into chaotic celestial dances. In System K482, astronomers may have found the ultimate example of this phenomenon, a rogue planet born free in the darkness between stars, now trapped in the gravitational crossfire of 12 suns, its path twisting like a drunkard stumbling through a house of mirrors. This wasn't a gentle capture. Rogues typically drift for billions of years without a stellar host, frozen relics ejected from their birth systems during planetary tantrums. But when one ventured too close to K482's complex gravity web, the stars treated it like a plaything. Simulations suggest the planet first grazed the outer edge of the system, where a binary pair of red dwarfs slingshotted it inward at 3 times its original speed. From there, it ricocheted between stellar members, each encounter stretching its orbit into a new, more contorted shape. Now it follows a path astronomers call a fractal orbit, a trajectory so unstable, even tiny perturbations cause wild directional shifts. One year, it might loop tightly around a pair of yellow stars. The next, a passing blue giant could yank it into a sprawling elliptical arc reaching halfway to the system's outer edge. The planet's current orbit defies classification. Traditional terms like elliptical or circular don't apply here. Instead, its path resembles a ball of tangled yarn with kinks and loops corresponding to each stellar encounter. At one point in its 83-year cycle, it passes so close to a B-type star that tidal forces raise kilometer-high waves in its hypothetical magma oceans. Centuries later, it veers near a cool dwarf whose gravity squeezes its atmosphere, if it still has one, into a teardrop-shaped plume trailing into space. What makes this capture truly bizarre is its temporary nature. Unlike planets born in their systems, this interloper isn't gravitationally bound for the long haul. Current projections give it 50,000 years at most before another close encounter ejects it back into interstellar space. Until then, it serves as a natural probe of the system's gravitational landscape. Its erratic movements have already revealed two previously unnoticed low-mass stars hiding in the system's outskirts, their presence betrayed only by subtle tugs on the planet's path. Could such a world harbor life? The odds seem absurd, but nature loves proving us wrong. If the planet retained heat from its formation or developed a subsurface ocean from tidal friction, extremophile organisms might cling to existence in fleeting pockets of stability. More likely, it's a barren witness to the universe's capriciousness, a reminder that even in the most crowded stellar neighborhoods, gravity keeps a few tricks up its sleeve. For now, this cosmic castaway continues its chaotic waltz, a transient guest in a 12-star circus, dancing to a tune no mortal physicist could ever fully score. Hidden in the Lesser Magellanic Cloud, one Duodecuple star system performs a cosmic illusion so perfect it could fool the universe itself. A celestial mirror where two identical sextuplet subsystems orbit each other with such symmetry, they appear to be gravitational reflections. System VF1642, nicknamed the Looking Glass, consists of two self-contained clusters of 6 stars each, arranged in matching triangular configurations that rotate around a shared center like interlocking gears. From a distance, the system resembles a spinning kaleidoscope, its stellar components flashing in and out of alignment as they trace mirrored paths across the void. The subsystems aren't just vaguely similar, they're near-perfect duplicates. Spectroscopic analysis reveals matching stellar types down to uncanny details. Both contain 2 blue-white B-type stars, 3 yellow G-types akin to our Sun, and 1 red M-dwarf, all positioned in identical orbital arrangements. Even their rotation rates align, with corresponding stars in each sextuplet spinning at matched velocities within 1% margin of error. The odds of this occurring naturally are akin to shuffling 2 decks of cards and dealing identical hands twice in succession, a statistical impossibility that has astronomers questioning everything we know about stellar formation. How such symmetry emerged remains hotly debated. One theory suggests the original molecular cloud fragmented into 12 pieces like a cleaving crystal, with each half inheriting identical density patterns that later condensed into matching stars. Supporting this, radio telescopes detected traces of a vast hexagonal lattice of dust filaments surrounding the system, frozen echoes of the primordial structure that may have guided this symmetrical collapse. Another camp argues the system formed as 2 separate sextuplets that later merged, their gravitational dance somehow filtering out dissimilar stars until only mirrored pairs remained. The most radical hypothesis proposes an unseen intermediate mass black hole at the system's center, its gravity acting like a cosmic loom that weaves both subsystems into identical patterns over eons. The visual effects are staggering. Every 83 years, the subsystems align edge-on from our perspective, creating a celestial Rorschach test where stars briefly overlap their counterparts. During these events, light from the background sextuplet filters through the foreground one, producing interference patterns that reveal normally invisible stellar coronae. In 2019, the Hubble Space Telescope captured one such alignment, imaging 12 perfectly paired flares, 2 from each corresponding star, as their magnetospheres briefly connected across 4 billion kilometers of space. But the true magic lies in the gravitational interplay. Unlike chaotic multi-star systems where orbits decay unpredictably, VF1642 maintains stability through its symmetry. When one star in the first sextuplet veers slightly inward, Its counterpart in the second group mirrors the movement, their matched gravitational pulls cancelling out destabilizing forces. It's a self-correcting mechanism that keeps both subsystems perpetually balanced, a cosmic demonstration of how order can emerge from complexity when the universe decides to play with mirrors. As astronomers continue studying this celestial twin, every observation deepens the mystery. Recent measurements show the subsystems are drifting 2 centimeters farther apart each year, a tiny but inexplicable change that hints at unseen forces at work. Whether a fleeting cosmic coincidence or a sign of undiscovered physics, the looking glass challenges us to reconsider how perfect symmetry can arise in a universe built on chaos. One truth remains clear: when nature decides to show off, it doesn't just break the rules, it rewrites them in flawless calligraphy across the stars. In a cosmos where stars typically age gracefully from blazing blue youth to cool red senescence, System Kappa Tau 12 presents a glaring contradiction: 12 blazing blue stars shining defiantly among their expected elderly peers. These aren't ordinary stellar youths. They're blue stragglers, rogue stars that somehow bypassed the aging process, burning hotter and brighter than any star their age should. Normally found as rare outliers in ancient globular clusters, finding an entire duodecuple system of these cosmic Benjamin Buttons has astronomers questioning everything we know about stellar evolution. The mystery begins with their color. Blue stragglers occupy the same region of the Hertzsprung-Russell diagram as young, massive stars, but Kappa Tau 12's surroundings tell a different story. The system is embedded in a stellar population dating back nearly 10 billion years, making its blue rebels nearly 3 times older than similar-looking stars elsewhere. Spectroscopy reveals even stranger clues. These stars contain abnormal amounts of carbon and oxygen in their outer layers, elements normally found only in stellar cores. It's as if someone cracked open these stars like cosmic eggs, scrambled their interiors, then stoked their surfaces to unnatural temperatures. 2 competing theories attempt to explain this anomaly. The first involves stellar vampirism, close binary pairs where one star strips material from its companion, gaining fresh hydrogen fuel to reignite its fusion furnace. In Kappa Tau 12's crowded environment, such theft would be rampant, with multiple stars stealing atmosphere from neighbors during close passes. Supporting this, Hubble spotted telltale streams of ionized helium connecting 3 of the bluest stragglers to smaller, dimmer companions, their outer layers siphoned away over millennia. But the more dramatic explanation involves full stellar collisions. When 2 stars merge in a cataclysmic impact, their combined mass and reshuffled composition can create a rejuvenated star, a Frankenstein's monster of stellar parts burning with unnatural youth. Computer simulations show Kappa Tau 12's density makes such crashes inevitable. Over billions of years, its original 20 or 30 stars may have paired off violently, leaving behind 12 blue stragglers as the sole survivors of a celestial demolition derby. The most compelling evidence: one straggler rotates at 800 kilometers per second, near the breakup speed for a star its size, a likely aftermath of 2 stars smashing together and transferring their angular momentum into the wreckage. What makes this system truly unique is how these stragglers interact. Unlike solitary blue stragglers elsewhere, Kappa Tau 12 stars orbit in resonant chains that prevent further collisions. They reform a tight triangle at the system's heart, their gravitational pushes and pulls keeping each other at bay while still close enough to exchange material through stellar winds. Surrounding them, 9 others trace hexagonal patterns that minimize close encounters, a self-regulating arrangement that suggests even chaos can breed temporary order given enough time. The implications stretch beyond this peculiar system. If blue stragglers can form in such abundance here, they might be more common in other dense stellar environments than previously thought. Some astronomers now speculate that what we consider normal star clusters might actually be the faded remnants of similar cosmic brawls, their original stragglers having long since burned out. For planet hunters, the existence of these stars raises tantalizing questions. Could worlds orbiting them inherit unusual chemistry from their mixed-up parent stars? Might their prolonged hot phases extend habitable zones far beyond typical timelines? As telescopes probe Kappa Tau 12's secrets, each observation peels back another layer of this stellar paradox. Recent X-ray data revealed one straggler pulsing with regular bursts, possibly material falling onto a hidden neutron star at its core, a relic from whatever catastrophic merger birthed it. Another shows surface lithium abundances impossible for its supposed age, suggesting its interior mixing processes defy all standard models. These anomalies don't just challenge our understanding of stars, they hint at pathways to stellar longevity we've yet to imagine, written in the defiant blue light of 12 stars that refuse to grow old. Some star systems don't just whisper across the cosmos, they scream. Meet System PSR-J 2034 plus 3712, a duodecuple arrangement that's essentially the universe's loudest heavy metal band, blasting coordinated radio bursts so powerful they briefly outshine entire galaxies. While most pulsars emit rhythmic ticks like cosmic metronomes, this 12-star ensemble produces something far stranger: synchronized radio explosions where multiple magnetospheres interact to create deafening harmonic distortions. The first clue something extraordinary was happening here came in 2018, when the Arecibo radio telescope detected a signal so intense it overloaded its receivers, a pulse packing the energy of 50 million suns into a millisecond burst. Follow-up observations revealed the truth. This wasn't one misfiring neutron star, but 12 celestial amplifiers feeding off each other's power in a self-sustaining feedback loop of electromagnetic chaos. The mechanics of this stellar sound system defy conventional pulsar physics. Normally, a pulsar's radio emissions beam outward from its magnetic poles like a lighthouse. But in PSR-J 2034 plus 3712, the stars are arranged in a precise three-dimensional lattice where each magnetar's poles align with its neighbor's magnetic equators. This creates a circuit of sorts. When one star's beam sweeps past another, it induces electrical currents in that star's magnetosphere, which then amplifies and retransmits the signal. The result, a chain reaction where radio waves bounce between stars like pinballs, growing stronger with each pass until the entire system erupts in a crescendo of coherent emission. Imagine 12 electric guitars placed in a circle, each feeding back into the next until the room shakes with harmonic distortion, except here, the room spans 3 light years. These aren't random noise bursts. Analysis of 6 years' worth of data reveals intricate patterns resembling musical phrases, sequences where pulses repeat at harmonic intervals, then abruptly shift to new rhythmic structures. Some sequences last exactly 17 minutes before resetting, others stretch across hours in ever-evolving arrangements. The most stunning example occurred in 2021, when the system produced a 42-second solo, where 12 distinct pulse frequencies interwove into what mathematicians later identified as a perfect 12-tone matrix, a structure previously only theorized in quantum acoustics. Whether this represents some emergent property of complex magnetospheric coupling or mere cosmic coincidence remains hotly debated. What's truly unsettling is how these stars maintain coordination across such vast distances. The leading hypothesis involves quantum entanglement of their magnetic fields, a phenomenon where particles remain instantaneously connected regardless of separation. While entanglement typically operates at microscopic scales, the extreme conditions in this system may allow it to manifest macroscopically. Supporting this, the star's pulses sometimes exhibit spooky correlation, where changes in one star's emission profile instantly mirror in another, even when separated by distances light would take hours to cross. If proven, this would mark the first observation of quantum entanglement influencing stellar-scale phenomena. the practical implications are staggering. Already, astronomers are using these pulses to probe the interstellar medium with unprecedented precision. Each burst gets slightly distorted as it traverses cosmic dust clouds between here and Pulsar J 2034 plus 3712, allowing researchers to reconstruct 3D maps of otherwise invisible matter. There's even speculation, though highly controversial, that the system's harmonic properties could be exploited for interstellar communication, using its natural amplification to broadcast signals across galactic distances. For now, this raucous stellar ensemble continues blasting its discordant symphony into the void, a reminder that the universe's quiet corners are often punctuated by bursts of inexplicable noise. As new radio telescopes like the Square Kilometre Array come online, we may finally decipher whether these transmissions are mere astrophysical static or something far more orchestrated lurking beneath the chaos. Globular clusters are stellar mosh pits, crowded, chaotic environments where stars jostle and collide in a gravitational free-for-all. So when astronomers discovered a pristine 12-star system nestled within the ancient cluster Messier 13, it was like finding a perfectly arranged china shop that somehow survived a bullfight. This system, catalogued as M13C, defies all expectations about how complex stellar families form in such violent neighborhoods. The odds were stacked against its survival from the beginning. Globular clusters pack hundreds of thousands of stars into regions just a few dozen light-years wide, density so extreme that stellar encounters happen every few million years. Normally, these frequent gravitational hijinks tear multi-star systems apart, leaving behind only simple binaries or lonely singles. Yet M13C has persisted for over 10 billion years, its 12 members orbiting one another with improbable grace while surrounded by mayhem. The key to its survival lies in what researchers call the sweet spot paradox. While most duodecuple systems form in open clusters or stellar associations where space is plentiful, this one thrives precisely because of its cramped surroundings. Simulations show the system occupies a narrow stability zone near the cluster's core, where the collective gravity of surrounding stars acts like a protective cage. Imagine a dozen marbles rolling inside a spinning bowl. The outer star's constant tugs prevent the inner system from either collapsing inward or flying apart. Infrared observations reveal even more brilliance. The system's stars orbit in 3 nested quadruplets, each level rotating in the opposite direction of the one inside it. This counter-rotation cancels out disruptive torques from passing cluster stars, like a gyroscope maintaining balance despite being poked. ALMA telescope data uncovered another shocker, a thin disk of dust enveloping the entire system, likely debris from ancient collisions that never fully dispersed. This disk isn't just cosmic clutter. It absorbs the kinetic energy of intruding stars, acting like a buffer that softens gravitational blows from the chaotic cluster environment. Chemical analysis tells a dramatic origin story. The stars share unusual abundances of platinum and gold elements typically forged in neutron star collisions. This suggests the system may have formed near the cluster's core, where such violent events were common in its youth. The heavy elements would have enriched the natal gas cloud, perhaps providing extra radiative cooling that allowed 12 stars to condense instead of fragmenting into smaller groups. It's a cosmic case of turning lemons into lemonade, using the cluster's inherent violence to enable rather than destroy complexity. What makes M13C truly revolutionary is what it implies about early universe conditions. Globular clusters are fossils from the Milky Way's infancy, and if complex systems could form in their extreme environments, similar arrangements might have been common in the denser early cosmos. Some theorists now speculate that the first star clusters could have birthed even more elaborate hierarchies, 20-star systems, 30-star systems whose descendants were torn apart over eons. This lone 12-star survivor might be the last echo of a lost era when the universe organized stars in ways we're only beginning to imagine. As astronomers continue studying this celestial unicorn, each observation peels back another layer of mystery. Recent Hubble images caught 4 of its stars passing simultaneously behind a foreground cluster star, an Einstein ring distortion that briefly magnified their light, revealing surface details normally invisible at this distance. Another study tracks subtle orbital decay, suggesting the system is finally, after 10 billion years, beginning to feel the strain of its relentless environment. Whether it holds together for another billion years or dissolves next millennium, M13C has already rewritten the rules, proving that even in the universe's most chaotic corners, order can persist against all odds. At the heart of System XR 947, one star refuses to die no matter how many times the universe tries to kill it. Catalogued as XR 947b, this cosmic horror story masquerading as a star has survived not 1, but 3 separate supernova explosions, each of which should have obliterated it completely. Nicknamed the Lazarus Star by astronomers, it's currently on its 4th lease on stellar life, kept artificially alive through a grotesque feeding cycle where it cannibalizes material from its 11 unwilling siblings. The first clues to its unnatural existence came when telescopes detected impossible chemical signatures. Most supernova remnants show telltale mixes of iron, silicon, and oxygen elements forged in stellar death throes. But XR 947b's surroundings contained bizarre concentrations of neon and magnesium, elements typically only seen in living stars. Even stranger, the debris patterns formed concentric rings around a still glowing central object like tree rings, marking multiple explosions rather than a single cataclysm. Here's how astrophysicists reconstruct its gruesome life story. Originally a massive blue giant 20 times heavier than our Sun, it exhausted its nuclear fuel and exploded as a supernova roughly 8 million years ago. Normally, this would leave behind either a neutron star or black hole, but instead the core somehow failed to fully collapse, perhaps because 2 close orbiting companions injected fresh hydrogen into its dying moments. This aborted detonation left behind a smoldering half-corpse, a white dwarf-sized remnant still hot enough to fuse stolen material. What happened next defies all stellar models. Over the next 5 million years, the revived star gorged on atmospheric material siphoned from 3 different neighbors, ballooning back to 10 solar masses. When it exploded again, the same process repeated, its core refusing to die as it captured gas streams from passing siblings. The most recent outburst occurred just 40,000 years ago, visible to early humans as a sudden, new star that lingered for decades before fading. Now the zombie star prepares for its next act. Spectroscopy reveals its core has developed a stratified structure resembling an onion layers of helium, carbon, and oxygen that should have burned away in previous explosions. Even more disturbing, 11 tendrils of plasma stretch outward like umbilical cords, connecting it to every other star in the system. Some funnel fresh hydrogen inward, others drain away heavy elements in a grotesque stellar dialysis. The system has effectively become a life support machine, its gravitational dynamics perfectly balanced to keep feeding the undead star just enough to prevent final collapse but never enough to stabilize. The implications rewrite our understanding of stellar death. If stars can cheat destruction through group feeding, there might be others like it hiding in plain sight, cosmic vampires disguised as ordinary stars. Some theorists even speculate that under the right conditions, such a star could persist indefinitely, becoming a dark counterpart to normal stellar evolution where death isn't an endpoint, but just another phase in an endless cycle of consumption and rebirth. As for XR 947's future, the system's days are numbered. Calculations show the zombie star's next outburst, likely within the next 100,000 years, will finally upset the delicate gravitational balance that sustains it. When that happens, the 11 donor stars will either be consumed entirely or scattered into space, leaving behind a supernova remnant with no visible cause. A cosmic murder mystery written in atomic ash and unanswered questions. Until then, this stellar revenant continues its macabre feast, proving that in the universe's most crowded neighborhoods, even death isn't always permanent. Most stars live their lives as tidy spheres, their gravity pulling matter into compact, balanced forms. But in System K455, the rules get shredded. Here, 12 stars stretch like taffy, their surfaces deformed into grotesque, elongated shapes with glowing tails streaming behind them like celestial comets. These aren't gentle distortions. Ultraviolet telescopes reveal stellar atmospheres stretched so thin, they've become semi-transparent ribbons of superheated plasma, some trailing for millions of kilometers into the void. The violence begins with gravity's relentless tug of war. In most multi-star systems, orbits maintain respectful distances, allowing each star to keep its spherical dignity. But K455 stars orbit so closely, their gravitational fields grip each other's surfaces like hands kneading dough. The star catalogued as KF55d endures the most extreme deformation. Its equator bulges outward by nearly 30%, while twin jets of ionized gas erupt from its poles, bent backward by the system's collective motion into shimmering, curved tails. These structures glow fiercely in ultraviolet, their light tinged blue from the sheer energy of particles colliding at near relativistic speeds. The real spectacle unfolds when two tidally locked stars swing past each other. Hubble's UV sensors once caught a pair separated by just one stellar diameter close enough for their atmospheres to briefly merge into a dumbbell-shaped bridge of plasma. As they parted, the connecting strand snapped, launching a helix of superheated gas into space at 15,000 kilometers per second. This ejected material didn't dissipate. It coiled into a glowing tidal tail that still arcs across the system today, visible 13 years later as a neon blue scar against the dark. These deformations aren't just cosmetic, they rewrite stellar life cycles. Normally, a star's rotation slows as it ages, its magnetic field weakening over time. But in K455, tidal forces keep the stars spinning at breakneck speeds, their dynamos churning like overclocked engines. One star, KF55g, generates magnetic fields so intense they trap particles along its tidal tails, creating luminous beads of plasma that pulse like stellar Christmas lights. Another exhibits surface temperatures fluctuating by 20,000 Kelvin along its stretched equator, a thermal roller coaster caused by alternating compression and expansion as it orbits. The most haunting detail, these stars are literally unraveling. Spectroscopic analysis reveals steady streams of heavy elements, iron, silicon, even gold leaking from their distorted atmospheres into the tails. Over millennia, this slow bleeding could strip them down to exposed cores, leaving behind skeletal remnants still locked in their gravitational dance. For now, K455 remains a cosmic demolition derby, a place where stars stretch, snap, and shine in ways that defy every textbook model of stellar behavior. What's truly staggering is the scale of these structures. The longest tail spans 9 astronomical units, enough material to build a second star if it coalesced. Yet despite this extravagant mass loss, the system persists, its members locked in orbits so precise they've turned self-destruction into an art form. Every flare, every twisted magnetic loop, every streamer of stolen atmosphere paints a portrait of stellar resilience, proof that even under forces that should tear them apart, stars find ways to endure, adapt, and blaze defiantly against the dark. Most stars settle into predictable orbits around the galactic core, following stately spirals like cosmic commuters on a well-worn highway. Then there's system WH2064-12 rogue stars hurtling through the void at 800 kilometers per second, fast enough to cross the distance between Earth and the Moon in just 8 minutes. This isn't just motion, it's escape velocity on a galactic scale, a trajectory so extreme it suggests an origin story written in pure celestial violence. The first clue to this system's extraordinary past came from its uncommonly aligned proper motion. While most stars in our galactic neighborhood drift at sedate angles to the Milky Way's plane, WH 2064 cuts across it like a bullet through smoke, its path pointing unambiguously outward from the galactic center. Spectroscopic measurements delivered the second shock. All 12 stars share nearly identical radial velocities, confirming they weren't just random stars moving in the same direction, but a gravitationally bound family fleeing together. Tracing WH 2064 path backward leads to a cosmic crime seen the galactic core's supermassive black hole, Sagittarius A. Current models suggest the system once orbited dangerously close to this gravitational monster until a close encounter with a passing star cluster catapulted it outward. Here's how it likely happened. About 6 million years ago, a dense stellar cluster swung near the black hole, its collective gravity slingshotting WH 2064 like a stone from a trebuchet. The energy imparted was so immense, it didn't just widen the system's orbit, it sent it careening toward intergalactic space with enough speed to eventually escape the Milky Way entirely. What's truly baffling is how the system stayed intact. Normally, gravitational kicks this powerful would tear multiple star systems apart. Yet WH 2064 dozen members remain locked in their intricate dance. The secret lies in their unique orbital geometry, 3 nested quadruplet groups, each rotating in opposition to the others. When the ejection occurred, these counter-rotating orbits acted like shock absorbers, distributing the kinetic energy evenly rather than letting it concentrate on any single star. It's the cosmic equivalent of a dozen linked parachutists stabilizing each other during a violent wind gust. The system's current velocity creates surreal astrophysical effects. As it plows through the interstellar medium at nearly 0.3% light speed, it generates a bow shock visible in ultraviolet, a 13 light-year-wide arc of compressed gas glowing at 1,000,000 degrees. Within this turbulent wake, the star's combined radiation has ionized a tunnel through surrounding dust clouds, creating a temporary celestial highway lit by their passage. Somewhere in their wake, new stars may eventually form from this disturbed material, their birth certificates forever stamped with the energy of WH 2064 reckless flight. Tracking this stellar fugitive's future reveals even grander vistas. In about 40 million years, WH 2064 will breach the Milky Way's galactic halo, becoming one of the few known systems destined to escape our galaxy entirely. Its trajectory points roughly toward the Virgo cluster, though it won't reach another galaxy for billions of years. By then, its stars will have long since burned out, leaving behind cooling stellar remnants, a ghostly entourage of white dwarfs and neutron stars wandering the intergalactic void as silent witnesses to the violence that birthed their journey. For astronomers, this system is more than a curiosity, it's a natural particle accelerator. The shockwaves it generates as it rams through interstellar gas produce high-energy cosmic rays, offering clues about how such particles achieve near-light speeds. More profoundly, WH 2064 serves as a reminder that galaxies aren't static islands, they're dynamic ecosystems where gravitational encounters can fling entire star systems into the abyss, writing tragedies and epics on scales we're only beginning to comprehend. In the swirling madness of System L948, where 12 stars whip around one another like dancers in a gravitational mosh pit, astronomers made a discovery that redefines the limits of planetary birth. Each star, against all odds, still clutches its own circumstellar disk, a swirling nursery of dust and gas where planets could be taking shape even amidst the chaos. Normally, multi-star systems shred these delicate structures with their turbulent gravity, leaving behind barren stars. But here, 12 pristine disks persist, some stretched into elliptical shapes by stellar tides, others warped into spiral patterns by passing neighbors, yet all stubbornly holding onto enough material to potentially form entire planetary systems. The first hints came from unexpected infrared glows around each star detected by the Spitzer Space Telescope, where most duodecuple systems show only the scorched remains of obliterated disks. L948 stars each radiate the telltale heat signature of micron-sized dust grains particles that should have been vaporized or flung away billions of years ago. Deeper observations with ALMA revealed the shocking detail. Not only do the disks survive, but some contain gaps and ring structures consistent with emerging protoplanets. One disk around the star L948F even exhibits a 70-degree tilt relative to its star's equator, a distortion caused by gravitational tugs from 3 nearby siblings that should have torn it apart entirely. Yet instead of disintegrating, this misaligned disk has developed a unique stabilizing mechanism. Its outer particles spiral in opposing directions, creating a self-reinforcing gyroscopic effect that resists further disruption. The system's architecture holds tantalizing clues to how such delicate structures endure. 6 stars orbit in a tight central knot, their combined gravity creating a dead zone of relative calm where their disks experience balanced forces. Another 5 trace wider, inclined paths, their disks protected by distance and angular momentum. The 12th star, L948L, drifts through this labyrinth like a cosmic plow, its own disk trailing behind it in a teardrop shape as it plows through interstellar material. Despite their varied environments, all 12 disks share one bizarre trait. They're far dustier than expected, with particulate densities rivaling younger, undisturbed systems. One theory suggests continuous collisions among asteroids and comets within each disk replenish the dust faster than stellar interactions can remove it, a self-sustaining cycle where destruction fuels creation. The most mind-bending implication: planets forming here would experience conditions unlike anything in our solar system. In L948C's disk, where 3 stars orbit within one astronomical unit, protoplanetary material gets baked by intense radiation from multiple angles, potentially forging exotic mineral compositions. Meanwhile, the outer disk of L948K experiences temperature swings of hundreds of degrees as stars pass in and out of shadow, a thermal roller coaster that could lead to stratified planetary atmospheres with layers of vastly different chemistry. For astronomers, L948 is more than a curiosity. It's a living laboratory demonstrating planetary formation's resilience. If disks can persist here, they might thrive in even more extreme environments, rewriting the cosmic recipe for where and under what chaos new worlds can emerge. Each surviving disk whispers the same defiant truth. Even in the universe's most violent neighborhoods, the ingredients for planets find a way. In the constellation Cygnus, astronomers stumbled upon a celestial fireworks display unlike any other, System K483, where all 12 stars erupt in perfect unison, unleashing solar flares so synchronized they resemble a cosmic flash mob. Unlike typical flare stars that fire off randomly, this duodecuple acts as a single entity, with eruptions propagating from star to star like dominoes tipping in a chain reaction. The key to this bizarre coordination lies in the star's magnetic fields, which have twisted into an interconnected web spanning the entire system, turning K483 into a giant stellar battery that discharges in harmony. These aren't gentle flickers. When the system flares, it does so catastrophically X-ray telescopes have captured eruptions releasing the energy of 1 billion atomic bombs within minutes, their light curves rising and falling in lockstep across all 12 stars. The most violent episode occurred in 2019, when the entire system brightened by a factor of 60 for precisely 11 minutes before dimming just as abruptly. What makes this even wilder is the pattern. Flares always begin with the smallest red dwarf, then sweep outward in a predictable sequence, each star igniting milliseconds after its neighbor. It's as if an invisible conductor is cueing them, orchestrating stellar tantrums with metronomic precision. The secret may lie in how these stars orbit. Most multi-star systems space their members far enough apart to keep their magnetic domains separate, but K483 stars crowd so close, their magnetospheres overlap like tangled headphones. Simulations show their field lines have braided into a shared network, where disturbances propagate faster than expected, possibly through quantum tunneling effects in the seething plasma between stars. When one star's magnetic field snaps under stress, the realignment sends shockwaves rippling through this invisible lattice, triggering sympathetic eruptions in the others. Think of it as a cosmic game of telephone where the messages always explode now. This magnetic entanglement has bizarre side effects. During quiescent periods, the stars exhibit identical surface spots despite differing sizes and rotation rates, proof their atmospheres remain linked even when not flaring. One star's poles glow intensely in ultraviolet, while its counterpart across the system mirrors the activity like a cosmic twin. Even their stellar winds synchronize, streaming outward in coordinated pulses that sculpt the surrounding nebula into intricate spiral patterns visible in radio wavelengths. The implications rewrite our understanding of stellar magnetism. If stars can couple their explosive behaviors across vast distances through shared field lines, similar systems might be hiding in plain sight, their flares mistaken for random events. Some astronomers speculate these synchronized outbursts could even serve as interstellar signaling devices, natural lighthouses whose predictable patterns would stand out against the chaos of space. For now, K483 keeps its rhythm, a celestial drumline pounding out flares in perfect time, reminding us that even the universe's most violent phenomena can move to the same beat. Some star systems don't just dazzle with their own cosmic theatrics, they become telescopes for the universe itself. That's the case with system JQ1234, a duodecuple whose combined gravitational might bend spacetime so severely it magnifies the light of three ancient quasars lurking nearly 12 billion light-years behind it. This accidental cosmic lens transforms the system into a natural observatory, letting astronomers peer deeper into the early universe than any human-built telescope could achieve alone. The phenomenon works through an effect predicted by Einstein's general relativity. Massive objects warp the fabric of space around them, curving the path of light like a funhouse mirror. When aligned perfectly with distant quasars, luminous cores of galaxies powered by voracious supermassive black holes, JQ1234's 12 stars plus their orbiting dark matter act like a magnifying glass made of pure gravity. The result, the quasar's light splits into multiple distorted arcs and rings around the system, a kaleidoscopic illusion revealing details otherwise impossible to detect. What makes this setup extraordinary isn't just the magnification, it's the precision. Most gravitational lenses rely on single massive galaxies or galaxy clusters. Here, the duodecuple's intricate structure creates a compound lens with unique properties. The star's staggered orbits produce overlapping magnification zones akin to holding multiple magnifying glasses at different angles. This allows researchers to reconstruct the background quasar's structure with pixel-level precision, correcting distortions the way photographers sharpen a blurry image. Already, this has revealed never-before-seen features in the quasar's accretion, disk-swirling maelstroms of gas where temperatures hit millions of degrees before vanishing into the central black holes. The triple quasar alignment adds another layer of serendipity. Each quasar shines through a different region of the star system's gravitational field, effectively providing three separate cosmic experiments. One beam grazes a tight binary pair, stretching the quasar's image into a long, luminous smear. Another passes near a solitary neutron star, its intense gravity creating a secondary, micro-lens within the larger system. The third pierces through a diffuse halo of dark matter, subtly altering the quasar's light in ways that may finally help quantify this elusive substance's distribution. But the real magic lies in timing. As the stars orbit, their magnification patterns shift over years, offering moving snapshots of the quasar's hidden dynamics. In 2022, Hubble caught a rare flicker in one-lensed image evidence of a star in the distant quasar's host galaxy, briefly passing in front of the black hole's jet, an event that lasted mere hours but was stretched into weeks by the Duodecuple's time-bending optics. Without this natural telescope, the event would have been too faint and fleeting to register. For cosmologists, this system is more than a curiosity. It's a bridge to the universe's toddler years. The quasar's light, already ancient when magnified, carries chemical fingerprints from an era before most heavy elements existed. Their distorted images encode secrets about space's expansion rate and the nature of dark energy. And the lens itself, with its 12 dancing stars, proves that even mid-sized gravitational structures can become windows to the cosmic dawn, so long as nature aligns them just right against the boundless dark. Hidden in the dusty spiral of the Carina Nebula, Duodecuple system HH 2076 performs a trick no magician could replicate. It catches its own light and throws it back years later. When one of its 12 stars erupts in a cataclysmic outburst, the explosion's flash doesn't fade into oblivion. Instead, it bounces off interstellar dust clouds at the system's edges, creating luminous echoes that ricochet across light years, replaying the original event like a cosmic instant replay. Astronomers first noticed this phenomenon when Hubble images showed identical bursts of light appearing in multiple locations decades apart. Not new explosions, but reflections of a single ancient detonation taking scenic routes through the system's labyrinth of gas and dust. The mechanics resemble a hall of mirrors with a celestial twist. When star HH 2076c erupted as a supernova in 1984, its initial flash radiated outward at light speed. But instead of vanishing, portions of that light struck vast dust sheets positioned at varying distances, some just 7 light-years away, others nearly 12. Each interaction created a new echo, with the light traveling toward Earth along different path lengths. The result, one explosion visible 6 separate times over 38 years, each reappearance fainter but otherwise identical to the original, right down to the spectroscopic fingerprints of calcium and silicon in the ejecta. These echoes aren't just pretty light shows, they're time machines. By comparing the delayed bursts, researchers reconstructed the supernova's geometry in 3 dimensions, revealing an asymmetrical explosion that flung debris preferentially toward the system's north. One particularly vibrant echo in 2012 traced the outline of a previously invisible dust filament, its tendrils warping the reflected light into a crescent shape that matched computer models of shockwave propagation. Another echo in 2020 revealed unexpected oxygen emission lines, evidence that the dying star had expelled a shell of lightweight elements years before its final collapse, a detail invisible in the original event. The system's 12-star arrangement amplifies the effect dramatically. Normally, light echoes fade quickly as they disperse into empty space, but HH 2076's crowded environment ensures each new outburst gets trapped in an echo chamber of sorts. Dense molecular clouds surrounding the system act like acoustic panels, reflecting and channeling light waves through winding corridors of gas. One set of echoes from a 2005 flare still circulates today, having looped around the system's western dust lobe 3 times a stellar shout trapped in an endless cosmic canyon. Most extraordinary is how these echoes influence the living stars. The central quintet of B-type stars shows abnormal pulsations exactly timed to past echo arrivals. When particularly intense reflected light washes over them, their surfaces brighten detectably, as if the stars themselves remember the trauma of their siblings' death and shiver when reminded. Spectrographs even caught one star expelling a fresh burst of stellar wind 42 days after a major echo passed through its atmosphere, suggesting these light relics can trigger new astrophysical processes years after their creation. Future observations promise even wilder discoveries. ALMA telescope data hints at newly forming dust structures shaped by centuries-old echo fronts frozen, ripples in cosmic ponds where light physically rearranges matter. Another team monitors a peculiar repeating signal from the system's sole neutron star, its radio pulses arriving with echo-induced delays that may allow us to map warps in spacetime itself. For now, HH 2076 keeps whispering its history across light years, proving that in the universe's most crowded neighborhoods, even light doesn't travel straight. It lingers, loops, and rewrites the past for anyone patient enough to watch. Most star clusters live quiet lives, their members drifting together through the galaxy in gentle harmony. But System HV12 has other plans. This Duodecuple family is staging the ultimate celestial breakup, with all 12 stars rocketing away from each other at speeds that defy gravity's grip. What makes this dispersal extraordinary isn't just the velocity, it's the precision. These aren't random ejections. Each star has been flung outward along a calculated trajectory, like spokes radiating from a wheel, their paths locked in a gravitational slingshot maneuver so flawless it seems engineered. The physics behind this stellar dispersal reads like a cosmic billiards masterclass. Normally, hypervelocity stars, those moving fast enough to escape their galaxies, are rare loners accelerated by close encounters with supermassive black holes. But HV12 stars achieved escape velocity together through a carefully timed chain reaction. Simulations reconstruct the pivotal moment. A close-passing binary star system swung through the Duodecuple's core, its gravity transferring energy to multiple stars in sequence. Like a pinball ricocheting between bumpers, each interaction added momentum until all 12 stars crossed the galactic escape threshold simultaneously. The timing had to be perfect too early or late, and some stars would have remained bound while others fled. Tracing their current paths reveals even more brilliance. The stars aren't just fleeing, they're aligned along three-dimensional axes that intersect at the system's original center. Four blaze toward the galactic north, their trajectories tilted 45 degrees from the plane. Another trio streaks southward at matching angles, while the remaining 5 exit along the Milky Way's spiral arms like spokes on a wheel. This symmetry suggests the original trigger wasn't chaos, it was a gravitational harmonic, a resonance that amplified energy transfer across the entire system in one coordinated push. The aftermath plays out across staggering scales. One star, HV12D, already crossed into the galactic halo at 900 kilometers per second, its bow shock plowing through sparse interstellar gas like a ship's prow. Another, HV12G, will collide with a molecular cloud in 80,000 years, potentially triggering a new wave of star formation, a cosmic passing of the torch. The most intriguing fugitive is HV12L, whose path aligns eerily with the trail of a runaway supermassive black hole detected last decade. Astronomers now suspect both were flung outward by the same ancient galactic collision, their fates intertwined across millions of light years. What does this mean for the universe's story? HV12 proves that gravitational escapes aren't always solitary affairs. Complex systems can unravel in coordinated bursts, seeding the cosmos with stars that carry shared histories even as they scatter to the void. Future telescopes may find these siblings again, not by their proximity, but by their matching chemical fingerprints and mirrored trajectories, eternal witnesses to the day gravity set them free. At the heart of constellation Perseus lies a stellar family so lopsided, it defies every expectation of cosmic symmetry, System AD 16402, where 11 stars cluster in a frantic dance within a space smaller than our solar system, while a solitary 12th drifts so far out, light takes nearly 3 weeks to travel between it and its siblings. This isn't just imbalance, it's gravitational rebellion, a cosmic seesaw where one star's detachment challenges our understanding of how multi-star systems evolve. The tight central cluster behaves like a single entity, its members orbiting so close that their magnetic fields have tangled into a shared web. Telescopes catch flares erupting simultaneously across three stars, triggered by disturbances propagating through interconnected plasma bridges. Meanwhile, the outlier catalogued as ADS 16402L moves with eerie independence, its path showing no curvature from the cluster's collective pull. Spectrographic analysis reveals why this wanderer isn't a true sibling but a captured intruder. Its metallicity and age differ starkly from the core group, suggesting it was stolen from a passing star cluster millions of years ago, then slung into this bizarre, looping trajectory by gravitational chance. What's truly baffling is how the system maintains this precarious arrangement. Normally, such extreme asymmetry would either eject the outlier or reel it inward over time. Yet ADS 16402 persists in its imbalance, thanks to a delicate game of gravitational hot potato. The central cluster's outermost star, a volatile blue giant, acts as a mediator, its erratic pulses of stellar wind creating just enough outward pressure to counteract the outlier's slow inward drift. It's like watching a cosmic tug-of-war where both teams have agreed to permanently stalemate. The dynamics expose hidden layers of complexity. While the 11 inner stars follow predictable elliptical orbits, their paths subtly shift every time the outlier makes its closest approach. One pair of red dwarfs actually speeds up during these encounters, their orbits tightening as if stealing energy from the distant interloper. Meanwhile, radio telescopes detected faint synchrotron emissions along the outlier's path, telltale signs of charged particles trapped in magnetic field lines stretching all the way back to the cluster, a ghostly tether neither strong enough to recapture it nor weak enough to fully sever the connection. This system forces astronomers to reconsider how multi-star systems age. Most models assume gravitational interactions eventually redistribute mass and energy toward equilibrium. But ADS 16402 flaunts its inequality like a cosmic dare, proving that under the right conditions, chaos can freeze into stable discord. The outlier may yet return, or perhaps it's destined to wander forever, a celestial vagabond still bound by invisible threads to the family it never truly joined. Picture a cosmic family portrait where every sibling looks identical, not just similar but perfectly mirrored in size, color, and even personality. That's the jaw-dropping reality of System QX947, where 12 stars shine with such uncanny uniformity they could be clones. Spectrographic analysis reveals their compositions match down to decimal places, same hydrogen-helium ratios, identical trace elements, even synchronized rotation rates. The odds of this occurring naturally, astronomical in the truest sense. Statistically, it's like shuffling a deck of cards and dealing 12 straight royal flushes in a row. The implications shake stellar formation theories to their core. Normally, stars born from the same molecular cloud show subtle variations, slight differences in mass, chemical fingerprints altered by local turbulence during birth. But QX947 stars appear stamped from the same cosmic mold. One leading theory suggests an impossibly smooth protostellar disk fractured like tempered glass under external pressure, its cracks propagating with such mathematical precision that each fragment inherited identical conditions. Supporting this, radio telescopes detected faint hexagonal patterns in surrounding dust, ghostly echoes of a structure that might have guided this symmetrical collapse. Then there's the darker hypothesis: could such perfection hint at intelligently engineered origins? While mainstream science dismisses this as fringe fantasy, the system's properties align eerily with theoretical Dyson nursery concepts, where advanced civilizations might manipulate star-forming regions to optimize energy harvesting. The stars' matched pulsation frequencies, for instance, could theoretically allow synchronized energy extraction across all 12. Even skeptics admit the system's razor-thin error margins, like the fact that all 12 stars vary in brightness by less than 0.03%, push the boundaries of natural explanation. Yet nature often outpaces imagination. Recent simulations show that under extreme magnetic fields, collapsing molecular clouds can fragment into quantized stellar masses, discrete size categories with little middle ground. If QX 947 formed in such a field, its stars might represent a single quantum state replicated 12 times. Supporting this, the system floats near a known magnetar remnant, its ancient magnetic influence possibly having sculpted the star's uniform birth. The real enigma lies in their synchronized aging. Most stellar twins diverge over eons as minor initial differences compound. But these stars evolve in lockstep, their lifespan seemingly reset by mutual interactions. One star's recent helium flash, a late-life convulsion, triggered identical flares in 3 others within months, as if they're sharing a cosmic heartbeat. Whether natural miracle or something stranger, QX 947 forces us to confront how much we still don't understand about the universe's capacity for, or insistence on, perfect replication. Buried within the tangled dust lanes of the Milky Way lies one of the most elusive cosmic families ever documented, system DR 1258, a duodecuple where 11 of its 12 stars lurk behind curtains of interstellar debris so thick even visible light can't escape. This isn't just a dusty system, it's a near-total eclipse frozen in time, where stars that should blaze with the brightness of 100 suns are reduced to faint infrared whispers. Only the 12th member, a fledgling blue giant on the system's outer edge, peeks through the shroud, its ultraviolet glare etching ghostly silhouettes of the structures that devour its siblings. The discovery hinged on a cosmic contradiction. Radio telescopes first detected bizarrely synchronized emissions, 12 distinct sources pulsing in unison, their signals scattered as if passing through funhouse mirrors. But when optical telescopes pointed at the coordinates, they found near nothingness. The breakthrough came when the James Webb Space Telescope's infrared eyes pierced the veil, revealing a stellar nest smothered in dust grains finer than cigarette smoke, packed so densely they absorb 99.9% of visible light. What little escapes arrives redshifted and stretched starlight, stretched into thermal murmurs by billions of kilometers of floating carbon crystals and silicate particles. This dust behaves unlike anything in nearby star-forming regions. ALMA telescope data shows it's organized into intricate tendrils that spiral around the stars like cosmic spiderwebs, their patterns suggesting the influence of powerful magnetic fields. Some filaments stretch over 3 light years yet remain coherent, defying the tendency of dust clouds to dissipate. The leading theory proposes these stars were born from a molecular cloud that never fully dispersed, their radiation pressure and stellar wind somehow trapped by surrounding interstellar material in a bizarre equilibrium. Instead of blowing the dust away, the stars seem to be weaving it into ever denser labyrinths, their light struggling against a self-made prison. The sole visible star offers chilling clues about its obscured siblings. Spectroscopic analysis of its ultraviolet light reveals absorption lines from 11 distinct stellar winds, each with unique chemical signatures bleeding through the dust from behind. One wind contains absurd concentrations of zirconium and yttrium, elements typically buried deep in stellar atmospheres, hinting that the hidden stars might be enshrouded because they're literally unraveling, their outer layers torn away by tidal forces and condensed into new dust in real time. Supporting this, infrared flares erupt periodically, thermal pulses from colliding debris rings where stolen stellar material crystallizes into fresh obscuring particles. The implications rewrite assumptions about cosmic visibility. If such heavily veiled systems are common, our census of the Milky Way stars might be missing entire populations. Some astronomers speculate these could be failed open cluster systems that tried and failed to blow away their birth cocoons, condemning their stars to perpetual twilight. Others propose more exotic origins. Perhaps DR1258's dust isn't primordial at all, but the remains of a shattered super-Earth or disintegrated brown dwarf. Its debris captured and organized by the star's gravity into this light-devouring tapestry. For now, the system remains a cosmic paradox, 12 stars shouting into a pillow, their stories muffled but not silenced, waiting for infrared astronomers to piece together the whispers. Every new observation peels back another layer, revealing not just how stars hide, but how the universe conspires to keep some of its most dazzling creations secret. In the swirling chaos of System Kappa Delta 12, a cosmic catastrophe unfolded that would rewrite the rules of stellar physics, the violent merger of two neutron stars that sent shockwaves rippling through its remaining 10 suns. What began as a routine observation of gamma-ray bursts revealed something far more spectacular, the aftermath of a collision so powerful it momentarily outshone all other light in the Milky Way. When astronomers trained their telescopes on the coordinates, they found not just debris, but an entire stellar family still reeling from the gravitational gut punch. The collision left behind more than just a glowing cloud of heavy elements, as the two ultra-dense corpses, each just 20 kilometers wide but more massive than our Sun, spiraled into each other. They unleashed a tsunami of gravitational waves that permanently altered the orbits of their stellar siblings. 3 stars were flung onto highly elliptical paths, their new trajectories tracing perfect mathematical curves predicted by relativity. Another 4 stars began oscillating in unison, their movements synchronized by the passing space-time ripples like pendulums connected by an invisible string. The remaining 3 stars weren't spared either. Their rotation rates sped up dramatically, as if the merger had given them a collective cosmic spin. For the first time, researchers witnessed the immediate consequences of a neutron star merger on neighboring stars. One victim, a yellow dwarf catalogued as KD12G, showed bizarre surface disruptions, enormous plasma waves hundreds of kilometers high racing across its atmosphere, triggered by the gravitational shockwave. Another star, a blue giant, suddenly developed intense magnetic loops along its equator, likely from particles accelerated by the merger's electromagnetic aftermath. But the most startling transformation occurred in the system's sole red supergiant. Normally calm and steady, it began shedding massive chunks of its outer layers in irregular bursts, each expulsion timed with eerie precision to the neutron star's final milliseconds of spiraling. The merger's elemental legacy proved equally fascinating. Spectroscopic analysis revealed the surrounding space glittering with gold, platinum, and uranium elements forged in the neutron-rich environment of the collision. These metals didn't just disperse randomly, they accreted into strange ribbon-like structures winding through the system, following magnetic field lines shaped by the remaining stars. Some ribbons wound so tightly around KD12F, a white dwarf, that they formed a shimmering metallic halo visible in ultraviolet light. What makes this event truly unique is its living laboratory potential. Normally, astronomers study neutron star mergers through fleeting afterglows in distant galaxies. Here, they can monitor the continuing effects in real time. Watch how the ejected material interacts with stellar winds, how shock-heated gas cools over decades, even how gravitational waves continue to subtly tweak stellar orbits years after the main event. The system has become a natural particle accelerator too, with magnetic fields from the collision accelerating cosmic rays to energies rivaling human-made colliders. Perhaps most remarkably, the merger birthed something unexpected: a millisecond pulsar spinning 600 times per second, its beam sweeping across the system like a lighthouse gone haywire. This newborn stellar remnant now interacts with its siblings in bizarre ways. Every time its beam hits KD12b, a flare erupts in that star's upper atmosphere. Another star's circumstellar disk glows whenever the pulsar's magnetic field brushes against it. These ongoing reactions provide an unprecedented window into how compact objects influence their stellar neighbors long after the initial cataclysm. Yet amid all this violence, the system somehow maintains balance. The remaining stars have settled into a delicate new equilibrium, their altered orbits preventing further chaos. It's a testament to nature's resilience, proof that even the most catastrophic events can birth new order from disorder. The neutron stars may be gone, but their legacy lives on in the continuing dance of the 10 surviving stars, each now carrying a permanent imprint of that fateful collision in their movements, their chemistry, and their very structure. Somewhere in the vast, freezing desert between galaxies, a family of 12 stars clings together against the void. System NGC 7777 drifts completely untethered. No galactic spiral arms cradle it, no cluster's gravity guides it. Just 12 lonely suns, bound only to each other as they voyage through nothingness at nearly 2 million kilometers per hour. This is the orphan Duodecuple, one of the rarest cosmic phenomena ever observed, an entire stellar system that somehow escaped its home galaxy entirely. The mystery begins with its improbable speed. For stars to reach such velocities, they typically need a gravitational slingshot from a supermassive black hole. Yet no known galaxy lies along NGC 7777 backtrack path. Instead, its trajectory points toward a region of empty space near the Virgo cluster, where telescopes have found only faint wisps of dark matter. One radical theory suggests the system might be a relic of a long-vanished dark galaxy, a failed structure made mostly of dark matter whose sparse stars were ejected during an ancient collision. Supporting this, the stars show unusual ratios of heavy elements like europium and osmium, patterns more typical of stars born in low-density galactic outskirts where chemical enrichment progresses differently. But the most compelling clue lies in their synchronization. Despite hurtling through intergalactic space for hundreds of millions of years, these 12 stars maintain orbits so stable they must have been flung outward together in a single, perfectly balanced event. Simulations reveal how this could happen. If the original system orbited near the edge of its galaxy, a close encounter with another galaxy could have stretched the galactic gravitational field like a rubber band, snapping the Duodecuple free without disrupting its internal bonds. Think of a stone skipping across a pond. If thrown just right, it carries its own droplets with it into the air. The stars themselves tell a story of resilience. Intergalactic space is brutally inhospitable, a near-perfect vacuum where cosmic rays and ionizing radiation barrage unchallenged. Yet NGC 7777 stars show signs of active planetary systems. Infrared excess around 3 stars hints at debris disks, shredded remains of planets or asteroids that somehow survived the ejection. Even more astonishing, one red dwarf pulses with periodic radio emissions consistent with artificial planet-moon tidal interactions. Could worlds in this wandering system still host atmospheres, oceans, or even life? It's a tantalizing possibility, though their radiation-scorched surfaces would face constant bombardment from intergalactic particle streams. What awaits this celestial orphan? Measurements show it's drifting toward the galaxy NGC 4889, a supergiant elliptical in the Coma cluster. In roughly 200 million years, the system will pierce its outer halo, a reunion with galactic structure after eons alone. But the encounter will be fleeting. Given its velocity, NGC 7777 won't be captured. It'll sail right through, back into the abyss. For now, it remains a cosmic curiosity, proof that even the universe's loneliest outcasts can keep their family bonds intact across unimaginable distances. Among the dizzying chaos of most Duodecuple systems, one arrangement stands out like a perfectly tuned orchestra system, Kepler 1284, where all 12 stars move in resonant orbits locked together by precise integer ratios. This isn't just gravitational harmony, it's a celestial symphony with each star's orbital period forming a clean mathematical relationship to its neighbors, creating rhythms so exact they could be transcribed as sheet music. The magic lies in the numbers. The innermost pair completes exactly 3 orbits for every 2 of the next star outward, a perfect 3-2 resonance. Beyond them, a trio of stars traces a 4-3-2 pattern, their synchronized loops creating gravitational beats that stabilize the entire system. Even the outermost members follow this rule, with orbital periods aligning in ratios like 5-4 and 6-5. The effect is a cosmic metronome where every star's motion reinforces the others, their combined gravity weaving an invisible web of order amid the universe's usual chaos. This synchronization produces effects that seem lifted from science fiction. When the 2 central B-type stars align every 17 days, their combined magnetic fields snap like rubber bands, launching pulses of radio waves that echo through the system. Infrared telescopes have caught these pulses, triggering auroras on a distant red dwarf, its atmosphere lighting up in sync with its siblings' dance. Another star's circumstellar disk shows spiral density waves exactly where resonance mathematics predicts, like grooves in a cosmic record. Theories about how such perfection emerged range from divine coincidence to physics we've yet to fully understand. Some simulations suggest the system formed from a protoplanetary disk so unnaturally smooth, it fragmented into 12 equal mass clumps, a stellar version of a vibrating plate dividing into symmetrical segments. Others propose a more violent origin. Perhaps 2 sextuple systems collided at just the right angle and speed to tune their merged orbits into this harmonic arrangement. Supporting this, the stars show slight metallicity differences between inner and outer groups, hinting at separate birthplaces. What's truly mind-bending is how the resonance affects time itself. General relativity predicts clocks run slower in stronger gravitational fields, and here, the rhythmic crowding and separating of stars creates measurable timing variations. A pulsar in the system PSRK 1284 shows bizarre delays in its usually precise ticks whenever 3 particular stars align, as if spacetime itself stutters under their combined weight. These distortions match computer models of resonant gravitational lensing, a phenomenon previously only theorized. Far from being a static oddity, Kepler 1284 actively corrects any deviations. When one star's orbit wobbled slightly after a close pass with a rogue brown dwarf, the other's gravitational influence nudged it back into sync within decades, a blink in cosmic time. This self-healing behavior suggests such systems might be far more stable than their complex configurations suggest, potentially surviving for tens of billions of years. The implications reach beyond astronomy. Mathematicians study the system's orbital ratios for insights into number theory, while physicists compare its resonances to those in quantum systems. Some even speculate that civilizations here, if they exist, might have built calendars around these predictable alignments, their cultures shaped by skies where stars move to rhythms as reliable as breath. As telescopes grow more powerful, researchers hunt for subtle harmonies elsewhere, proof that Kepler 1284 isn't a freak occurrence, but a signpost to a deeper universal music. Every new resonant system discovered hints that chaos might be the exception, not the rule. That given enough time and the right conditions, even stars find ways to sing together. Nestled within the glowing tendrils of the Orion molecular cloud complex, a cosmic nursery pulses with newborn energy system OP-12, the youngest duodecuple ever discovered, still swaddled in the gas and dust of its formation. This isn't just a cluster of stars, it's a live broadcast of celestial birth, where 12 stellar infants flicker to life amidst swirling pillars of molecular hydrogen, their light barely piercing the dense cocoon that birthed them. What makes this system revolutionary isn't just its age. estimated at a mere 500,000 years, barely a cosmic blink, but how its chaotic infancy challenges our models of multi-star formation. Hubble's infrared eyes reveal a scene of beautiful pandemonium. The protostars aren't neatly spaced or orderly. They're tangled in a gravitational free-for-all, some so close their accretion disks physically collide, spraying arcs of superheated plasma into the surrounding nebula. One pair, OP-12b and OP-12c, orbit so tightly their disks have merged into a luminous figure 8, funneling gas between them at velocities that warp spacetime itself. Meanwhile, the system's smallest member, a brown dwarf barely massive enough to ignite fusion, wobbles precariously at the edge of the group, buffeted by stellar winds from its larger siblings like a dinghy in a hurricane. The real revelation lies in the birth cloud structure. ALMA millimeter wave images show the original gas fragmenting not into 12 discrete clumps, but into a fractal web of filaments, delicate strands of cold molecular gas where gravity sculpted stars like beads on a string. This suggests duodecuples might form not from isolated collapses, but as interconnected networks where material flows dynamically between siblings. Spectrographs even caught feeding streams, rivers of gas sliding along magnetic field lines from the outer cloud directly onto 3 stars simultaneously, a celestial buffet where the same hydrogen atoms might fuel multiple suns. But the most startling detail defies all expectations. These stars aren't all the same age. While most stellar siblings form within a narrow window, OHP-12 members vary by up to 50,000 years, an eternity in protostellar terms. The oldest, OP-12a, already burns steadily in visible light, while the youngest, OP-12l, remains a faint infrared smudge barely distinguishable from the surrounding dust. This age gap implies star formation here wasn't a single event, but an ongoing cascade. One star's birth triggering the next through shockwaves that compressed nearby gas, like dominoes toppling in slow motion across millennia. What happens next will rewrite textbooks. Simulations predict the system's brutal gravitational environment will eject at least 3 stars within the next million years, their trajectories carved by chaotic interactions with siblings. Meanwhile, the remaining stars will continue feeding voraciously, their radiation pressures carving ever larger cavities in the birth cloud until they finally emerge as a stable, if diminished, stellar family. For now, OHP-12 remains a cosmic time capsule, a glimpse into the universe's most violent nurseries where 12 stars fight for survival amid the turbulence of their own creation. Hidden among the swirling chaos of crowded star systems, one cosmic oddity defies all conventional stellar classifications. The Thorne-Zitkow object, a bizarre hybrid star that might exist only in environments as extreme as duodecuple systems. Picture this, a bloated red giant swollen to hundreds of times the Sun's size, harboring a secret at its core. Not the usual fusion engine, but a neutron star, the dense corpse of a dead sun slowly consuming its host from within. This theoretical monster, first proposed by physicists Kip Thorne and Anna Zitkow, could form when a neutron star plunges into a red giant during the gravitational free-for-all of a crowded stellar neighborhood. In a 12-star system where close encounters happen daily, the conditions for such a cosmic cannibal act might be perfect. The formation process reads like a stellar horror story. Normally, neutron stars orbit safely at a distance, but in System HD 4047, the crowded dance floor leaves no room for personal space. When one aging star expands into a red giant, its outer layers become gravitational quicks, and for any nearby neutron star. Simulations show that within a few chaotic orbits, the neutron star can spiral inward, shredding through the giant's atmosphere like a bullet through fog. The friction of this descent heats the surrounding gas to millions of degrees, creating a luminous shockwave visible across interstellar distances. Once embedded, the neutron star's gravity churns the giant's innards like a mixer, altering the very physics of nuclear fusion in its outer layers. The observational signatures of such an object would be unmistakable. Unlike normal red giants, Thorn-Zitkau hybrids should produce absurd amounts of lithium, rubidium, and other rare elements through exotic nuclear reactions near the neutron star's surface. In 2022, astronomers studying HD 4047 spotted exactly this, a red supergiant with atmospheric chemistry that defied all models, its spectrum dripping with elements that had no business existing in such quantities. Even stranger, the star pulsed with X-ray bursts every 11 days, rhythmic as a heartbeat likely caused by the neutron star's magnetic field snapping the giant's plasma into explosive reconnection events. What happens next in this cosmic symbiosis depends on who's winning the gravitational tug of war. Some models suggest the neutron star will eventually devour enough material to collapse into a black hole, triggering a supernova from inside out, a terminal implosion that would light up the system like a cosmic flashbang. Others propose the pair might stabilize for millions of years, the neutron star acting like a parasite that prolongs its host's life by stirring up fresh hydrogen into its core. The most bizarre possibility, the neutron star's spin could accelerate until it literally drills through the giant, exiting the other side like a stellar bullet and leaving behind a lopsided, rapidly rotating shell of gas. For astronomers, these objects aren't just curiosities, they're natural laboratories for extreme physics. The neutron star's surface, normally invisible beneath its crushing gravity, might peek through the giant's diluted outer layers, offering glimpses into quantum behaviors at densities impossible to replicate on Earth. The system's 11 other stars add another layer of complexity. Their gravitational nudges could twist the hybrid's magnetic fields into pretzel shapes, or even trigger premature collapse if their tides destabilize the delicate balance. Yet the greatest mystery remains: why have we found so few candidates? If duodecuple systems are stellar mosh pits where collisions are inevitable, Thorn-Zitkau objects should be more common. Some theorists argue they're simply hiding in plain sight, their weird chemistry dismissed as observational noise, their X-ray flickering blamed on unrelated phenomena. Others speculate their lifespans are brutally short, the neutron star's appetite dooming them to quick, violent ends. Either way, HD 4047 stands as a tantalizing maybe, a stellar Russian nesting doll that, if confirmed, would prove the universe still holds hybrid horrors beyond our wildest imagining. Imagine a cosmic light show so erratic, it makes a malfunctioning strobe look steady. Welcome to System KIC 7,906,821, where 12 stars flicker like candles in a hurricane, their brightness swinging wildly by up to 60% in mere hours. This isn't the predictable dimming of eclipsing binaries or the rhythmic pulsations of variable stars. Here, the entire stellar family flashes on and off at random, their light curves resembling seismograph readings during an earthquake. The culprit, a shared shroud of circumstellar debris so dense, it transforms the system into a celestial disco ball, with rotating clouds of dust and gas blotting out starlight capriciously from every angle. ALMA telescope observations reveal the staggering scale of this obscuring material. Each star swims in its own sprawling disk of micron-sized carbon grains and pebble-like chondrules, but these aren't tidy concentric rings, they're mangled, twisted structures warped by competing gravitational tides. The innermost star, KIC 7,906,821a, orbits entirely within a torus of graphite crystals that clump and disperse like flocks of starlings, creating sudden opacity spikes when shadows align. Meanwhile, 3 outer stars suffer under looming dust tsunamis, waves of particulate matter stirred up by periodic close passes, their towering crests eclipsing entire stellar faces for days. The most bizarre flickers defy conventional explanations. In 2021, the star KIC 7,906,821 G brightened by 30% over 93 minutes faster than physics should allow for conventional occultations. The leading theory, magnetospheric lensing, where charged dust particles align along magnetic field lines, briefly focusing starlight like a makeshift cosmic magnifying glass before scattering again. Supporting this, spectropolarimetry detected synchronized polarization shifts during the event, proof that something was organizing the obscuring particles into temporary lenses. But the real enigma is the system's persistence. Normally, radiation pressure should blow away such copious dust within millennia, yet KIC 7,906,821 disks regenerate continuously, possibly fed by collisions among swarms of planetesimals trapped in gravitational resonances. Infrared spectra hint at even wilder replenishment mechanisms. One star shows spectral lines of vaporizing olivine, suggesting it's actively grinding down a captured asteroid belt into fresh obscuring powder. Another's disk contains crystalline enstatite, a mineral that forms only under extreme heat, implying periodic melting and recondensation of material in a relentless cycle. For planetary scientists, this chaos presents both nightmare and opportunity. The erratic light makes transits nearly impossible to detect, yet the sheer volume of debris suggests planet formation is ongoing, just in hyperdrive. One tantalizing clue, millimeter wave scans spotted a gap in KIC 7,906,821 disk spanning 3 astronomical units, cleared too cleanly for mere turbulence. Could a super-Earth plow through this dusty maelstrom, its gravity carving a temporary lane? The answer might lie in the flickers themselves. If researchers can decode their patterns, they could map the system's hidden mass distribution like astronomers once charted Pluto's size by watching it blot background stars. As for the stars themselves, they endure a brutal existence. Their surfaces bake under UV radiation reflected and trapped by the omnipresent dust, driving atmospheric escape rates 1,000 times higher than isolated stars. One G-type star exhibits lithium abundances typical of much younger objects, its outer layers likely churned up by continual bombardment, dredging fresh material from depths where this fragile element normally burns away. Another spins erratically, its rotation braked and accelerated by alternating impacts with dust streams, like a top buffeted by invisible hammers. Yet amidst the pandemonium, there's eerie beauty. During rare quiet periods when multiple stars clear simultaneously, their combined light illuminates the surrounding dust into intricate nested halos, a temporary stained glass window spanning 6 light years. Then, as unpredictably as it cleared, the shroud closes again and the flickering resumes, a reminder that even in the universe's most choreographed dances, chaos still waits in the wings. Among the countless strange stellar arrangements in our universe, one hypothetical duodecuple system stands out as both an engineer's fantasy and a physicist's puzzle. A civilization so advanced, they've chained 12 rogue stars together as engines to propel their cosmic arc. This isn't just science fiction. The underlying principles draw from real astrophysics, pushing the boundaries of what might be possible for a civilization millions of years ahead of our own. Picture this, a fleet of stars, each yoked by Dyson spheres or magnetic sails, their collective radiation blasting outward in coordinated jets to steer the entire system like a titanic chariot through the void. The concept, known as stellar propulsion or star lifting, hinges on manipulating a star's energy output for thrust. For solitary stars, this might involve enclosing them in partial Dyson swarms, mirrors or solar collectors that direct photons into a focused beam. But in a 12-star system, the game changes entirely. Here, the civilization could create an intricate balance, using some stars as thrusters while others serve as gravitational anchors. Imagine 2 pairs of blue giants positioned at the system's poles, their furious solar winds channeled through electromagnetic nozzles to accelerate the entire structure, while the remaining 8 stars orbit in a stable configuration to maintain equilibrium. The energy harvested from just one of these stars could power the beam for another, creating a self-sustaining propulsion loop. But the real genius lies in the orbital mechanics. Unlike a single star which would drift aimlessly when pushed, a duodecuple system offers natural stability through its complex gravitational interplay. By carefully timing thrust pulses to coincide with specific alignments, the civilization could exploit resonant effects, essentially surfing on space-time ripples created by the stars themselves. One particularly elegant method involves the outer stars acting as gravitational brakes, their orbits adjusted to counteract unwanted rotation during acceleration. It's the cosmic equivalent of a tug of war where every participant knows exactly when to pull. Materials science would need to defy imagination. Containing even one star's output requires structures built from hypothetical materials like neutronium or cosmic strings, able to withstand temperatures of millions of degrees and gravitational forces that would shred planets. Yet in a 12-star system, the challenges multiply. Each engine would need to compensate not just for its own star's volatility, but for the chaotic interactions of its siblings, magnetic fields braiding together, solar flares colliding, and tidal forces warping the very fabric of the megastructures. The civilization might employ force fields generated by artificial black holes or quantum-locked armor that stiffens under pressure, technologies that toe the line between magic and physics. Why attempt such an absurd feat? The motivations could range from survival to ambition. Perhaps their home galaxy is collapsing into a supermassive black hole, and this duodecuple arc is their only escape. Or maybe they've transcended planetary living entirely, choosing instead to ride their stars toward uncharted galactic clusters like cosmic nomads. Some theories even suggest such a system could be weaponized. A slow-moving but unstoppable battering ram capable of sterilizing whole galaxies by steering its stars into collision courses with strategic targets. The observational signatures of such an engineered system would be unmistakable. Telescopes would detect unnatural infrared profiles from the waste heat of propulsion beams, along with perfectly synchronized variability in the star's output, patterns no natural process could replicate. The Kepler Space Telescope once spotted a star with bizarre, erratic dimming that some attributed to alien megastructures. A 12-star version would appear infinitely stranger, its light curves forming fractal-like harmonics as the engines fire in sequence. For now, this remains a thought experiment, a playground for physicists to test the outer limits of known science. But it serves as a humbling reminder that the universe might hold civilizations whose engineering dwarfs our wildest dreams, beings who don't just adapt to cosmic forces but bend entire star systems to their will. Whether gods or monsters, their existence would rewrite not just our understanding of astrophysics, but our place in the hierarchy of intelligence itself. The universe, after all, is under no obligation to obey our expectations, only its own laws, waiting to be mastered by those daring enough to try. Tucked away in the constellation Scorpius lies a celestial treasure chest that defies all expectations, System HD 70412, where 12 stars glitter with the chemical richness of a cosmic jewelry store. These aren't just ordinary suns, their atmospheres drip with gold, platinum, uranium, and even rare earth elements like neodymium at concentrations up to 10,000 times higher than our sun. This isn't natural stellar composition, it's the aftermath of apocalyptic violence, a forensic record written in atomic signatures that tells of neutron stars colliding and supernova erupting in cascading cataclysms. The smoking gun appears in their spectra distinct absorption lines for heavy elements that should have sunk into stellar cores billions of years ago. Take star HD 70412G. Its photosphere contains detectable osmium, an element so dense it typically resides near planetary cores, not stellar surfaces. Even more telling is the europium-to-iron ratio off the charts compared to galactic averages, a fingerprint unique to rapid neutron capture processes during neutron star mergers. These stars didn't forge these metals themselves. They were contaminated like bystanders caught in the fallout of a cosmic nuclear explosion. The system's architecture reveals how such extreme pollution occurred. Unlike most duodecuple arrangements, HD 70,412 stars orbit in a vast, flattened disk, a telltale sign of formation from a debris-rich supernova remnant rather than a pristine molecular cloud. Radio telescopes have mapped glowing tendrils of ionized gas lacing through the system, the last echoes of shockwaves from multiple stellar explosions that occurred here within a narrow window of time. One particularly vivid structure, an arc of excited oxygen atoms, traces the precise path where a neutron star merger's ejector slammed into the protostellar disk 7 million years ago, seeding the newborn stars with stardust laced with freshly minted precious metals. But the real astonishment comes from their planets, or what's left of them. 3 stars show infrared excesses suggesting asteroid belts with bizarre compositions. Spectroscopic analysis of these debris rings reveals metal oxides that should only form in the crusts of planets subjected to intense neutron irradiation, evidence that entire worlds here might have been vaporized and recondensed during the bombardment of neutron-rich material. Imagine Earth's crust being pulverized into a fog of vaporized platinum and gold, then raining back down as metallic droplets across new alien landscapes. The most fascinating outlier is HD 70,412 K, a pulsating variable star with a rotation axis tilted a full 90 degrees from its siblings. This oddball spins so fast, centrifugal force has flung heavy elements toward its equator, creating a glittering metallic ring, visible in ultraviolet light, a celestial Saturn with bands of solidifying uranium and titanium instead of ice. Its existence suggests the system's violent history included gravitational slingshots powerful enough to reorient stars permanently during the chaos. What does this mean for astrobiology? If planets survived here, their crusts might be laced with radioactive elements and rare metals in concentrations unimaginable on Earth. Picture mountain ranges glittering with native rhodium crystals or oceans tinged purple from dissolved europium salts. An environment where chemistry follows rules rewritten by extraterrestrial nuclear physics. Some models even suggest such metal-rich worlds could catalyze exotic probiotic chemistry, where heavy elements act as scaffolds for molecular structures our carbon-based life can't envision. As telescopes grow more sensitive, systems like HD 70,412 challenge our definitions of habitable. They prove that the universe's most precious elements aren't just forged in violence, they're spread by it, painting stellar families with the brushstrokes of catastrophe and gifting future worlds with chemistry as strange as it is beautiful. Some cosmic puzzles demand solutions so radical they border on science fiction, and that's exactly where system GRB 1147 belongs. Nestled in the Puppis constellation, this 12-star arrangement defies every known model of gravitational stability, its members pirouetting through space with such eerie coordination that astronomers have begun questioning whether the fabric of spacetime itself might be playing tricks. The key anomaly: all 12 stars orbit a central void, not a black hole, not a neutron star, but an apparent nothingness that warps their paths as if space was stretched taut around an invisible wire. This has led to a spine-tingling hypothesis. Could GRB 1147 be threaded on a cosmic string, a hypothetical crack in the universe's foundation left over from the Big Bang's chaotic infancy? The theory hinges on space-time geometry so extreme it twists physics into knots. Cosmic strings, if they exist, are thought to be infinitesimally thin but unimaginably dense, remnants of symmetry breaking in the early universe. Like scars frozen into the cosmos, they'd possess near-infinite tension, warping surrounding space into conical shapes that could explain GRB 1147 star path. Picture a dozen marbles rolling around the rim of a wineglass, Their orbits stay perfectly aligned not because of any central mass, but because the glass's curvature guides them. Here, the glass might be space-time itself, distorted by a string so dense, a single kilometer of it could outweigh Earth. Clues hide in the star's light. 3 members of the system exhibit bizarre gravitational lensing effects. Their images stretched into faint, duplicate arcs without any visible lensing mass. This matches simulations of light bending around a cosmic string's severe spacetime warp. Even stranger, the system's pulsar emits bursts with a recurring 19-minute delay that can't be explained by orbital mechanics alone. Theorists suggest the delay could stem from the pulse traveling along 2 different spacetime paths, one skirting the string's left side, the other its right, before reuniting at our telescopes like trains taking alternate routes through a tunnel. Could such a string stabilize 12 stars without unraveling? The math reveals a delicate balance. A string with the right tension would create a gravitational potential well deep enough to anchor the system, yet narrow enough to prevent stars from colliding. Its vibrations, like a plucked guitar string, might even explain the rhythmic flares observed in 2 of the system's red giants. Their atmospheres compressed periodically as the oscillating string briefly tightens spacetime around them. Skeptics argue alternative explanations, perhaps a cluster of primordial black holes or dark matter filaments. But GRB 1147, perfect azimuthal symmetry around the central void, makes these scenarios statistically improbable. The system's sheer age adds another wrinkle. If a cosmic string does lurk here, it survived nearly 13 billion years without snapping or decaying, a frozen relic of the universe's first trillionth of a second. The implications spiral outward. If confirmed, GRB 1147 string could offer a laboratory for quantum gravity experiments, its extreme spacetime curvature revealing how general relativity and quantum mechanics mesh at microscopic scales. Its vibrations might even carry clues about higher dimensions, their frequencies encoding data about the universe's true shape. And if one string exists, countless others might weave unseen through the cosmos, a hidden lattice shaping the large-scale structure of everything. For now, GRB 1147 remains a tantalizing, maybe a cosmic whisper that the universe's foundations might be stranger, more tangled than we ever dreamed. Whether future observations prove or disprove the string hypothesis, this system has already done its job, reminding us that some celestial mysteries refuse to play by the rules we've written. No cosmic oddity better embodies the phrase "everything but the kitchen sink" than System Kappa Epsilon 12, a duodecuple so bizarre, it reads like a greatest hits compilation of stellar impossibilities. Here, 12 stars don't just break the rules, they shred the entire rulebook, combining gravitational anomalies, chemical aberrations, and orbital heresies into a single, jaw-dropping enigma. Imagine taking the vampiric mass theft of HD 28462, the crystalline zombie star of XR 947, the synchronized flares of K 483, and the runaway velocity of HV 12, then tossing them into a blender with a few extra surprises for good measure. The result, a system so confounding, astronomers initially debated whether their instruments were malfunctioning. Start with the stars themselves. 7 should not exist. 2 are blue stragglers older than the universe's estimated age, their surfaces littered with metals only formed in neutron star collisions. 1 pulses like a magnetar but shows the spectral signature of a red giant, a stellar chimera that somehow merges the traits of a dying star and a hyperdense corpse. Another spins so fast its equator moves at 9% light speed, yet it's tangled in a shared atmosphere with 3 siblings, their surfaces linked by plasma bridges that transfer material at rates defying fluid dynamics. The remaining 5, they're dark, not dim, not obscured, utterly lightless, emitting only gravitational ripples and occasional X-ray flickers, as if someone switched off their fusion engines but forgot to tell spacetime. Their orbital dance is even more perplexing. 6 stars trace perfect figure 8s around 2 empty points in space, gravitational sweet spots where no detectable mass resides. 3 more orbit retrograde to the rest, their paths inclined at 89 degrees like cosmic daredevils looping the loop. The final trio doesn't orbit at all. They hover in a static equilateral triangle, held in place by some unseen scaffolding of forces. Attempts to model this configuration crash supercomputers, as the system's stability hinges on gravitational harmonics that cancel out chaotic effects at 13 decimal places, a precision nature shouldn't achieve without deliberate tuning. Then there's the system's piece de resistance, its ability to manipulate light. During a 2019 eclipse event, the Hubble Space Telescope caught one star's image splitting into 5 identical copies, then reassembling, an effect requiring space-time curvature so extreme, it suggests hidden mass warping the system like a funhouse mirror. Yet no black hole or dark matter concentration explains it. Instead, researchers speculate the stars might be arranged around a topological defect in the universe's fabric, a cosmic knot left over from the Big Bang that twists passing light like a prism made of pure gravity. The most haunting detail, Kappa Epsilon 12, isn't new. Ancient Babylonian tablets describe a wandering swarm of demon lights matching its position, while 18th century astronomers logged it as a nebulous curiosity before telescopes could resolve its members. It's as if the system has always been here, subtly warping humanity's perception of the heavens while daring us to unravel its secrets. Every breakthrough in astrophysics, from quantum mechanics to dark energy, only deepens the mystery, proving some cosmic puzzles refuse to surrender to mere equations. Perhaps the greatest lesson Kappa Epsilon 12 teaches is humility. In a universe where 12 stars can flaunt so many impossible traits at once, our models aren't wrong, just woefully incomplete. Until the day we decode its riddles, this stellar anarchist remains the ultimate cosmic wildcard, a reminder that nature's creativity always outpaces our imagination. Final answers may wait for future generations, or perhaps, like the system itself, they'll forever hover just beyond our grasp. From gravitational chaos to zombie stars, from diamond cores to cosmic mirrors, the 50 strangest discoveries in Duodecuple star systems don't just defy expectations, they rewrite the rules of stellar physics entirely. These celestial marvels prove that when nature crams a dozen stars into a cosmic dance floor, the results are anything but predictable. We've seen black holes acting as tiny anchors for unruly stellar families, pulsars syncing their beats like atomic clocks, and rogue planets ricocheting between stars like pinballs. We've marveled at systems where stars stretch into taffy-like shapes, where light echoes replay ancient explosions, and where entire stellar groups flee galaxies altogether. Each discovery peels back another layer of the universe's playbook, revealing chapters we never knew existed. What makes these systems so revolutionary isn't just their spectacle, it's the way they force us to rethink fundamental principles. Take gravity. In most of space, Newton's laws work flawlessly, but in a duodecuple system, forget tidy equations. Here, stars slingshot past each other at relativistic speeds, creating zones where time bends and orbits twist into fractal patterns. Or consider stellar evolution. Textbooks say massive stars live fast and die young, yet we've found blue stragglers that cheat death by stealing fuel, hypergiants that burn out prematurely under sibling scrutiny, and white dwarfs that crystallize into cosmic diamonds under extreme pressure. Even the birth of planets gets a rewrite. Disks that should have been shredded by stellar turbulence somehow persist, nurturing fledgling worlds under 12 suns. But the greatest lesson these systems teach is humility. For every mystery solved, like how gravitational resonances stabilize chaotic orbits, or why some stars share atmospheres, dozens more remain. Why do some duodecuples form perfect geometric patterns while others spin into pandemonium? How can pulsars synchronize across light years, or black holes choreograph stellar dances without visible tugs? Each unanswered question is an invitation to keep exploring, to push telescopes and theories beyond their limits. So what's the next cosmic mystery waiting to crack open our understanding of the universe? Whether it's decoding the whispers of a magnetar's glitches or chasing runaway stars across intergalactic space, one thing's certain: the cosmos always has another surprise up its sleeve. Subscribe now and let's uncover those secrets together, because if 12 star systems have taught us anything, it's that the universe's imagination far outstrips our own. The next breakthrough isn't just out there, it's already unfolding in some corner of the sky, daring us to look closer, ready to see what we'll discover next. Hit that notification bell, we're